In the late 17th century, a quiet revolution unfolded in a world that still believed the heavens were governed by divine perfection. Isaac Newton walked into that uncertainty, carrying a method of thinking that combined mathematics, careful observation, and a conviction that nature followed rules that could be written in precise language. In the year 1687, he placed that vision onto the pages of the Principia, a work that shaped how humanity understood motion for centuries. In those pages, he described universal gravitation as a force acting between every pair of masses. According to his formulation, each object in the cosmos pulled on every other object with a strength that increased with their masses and weakened with the square of the distance separating them. For the first time, motion across the sky and motion on Earth shared a single explanation. The fall of an apple and the orbit of the moon were no longer mysteries of separate realms, but consequences of a force that reigned everywhere. The world tested his idea with relentless curiosity. Astronomers found that the predicted paths of planets matched their observations with astonishing accuracy. The strange elongation of Mars and the looping journey of Jupiter were no longer celestial puzzles, but natural outcomes of gravitational attraction. Comets, which had once been feared as omens, revealed their long, sweeping trajectories through the cold reaches beyond the known planets. The periodic return of Halley's Comet, an icy traveler whose orbit Newtonian mechanics foretold, became one of the earliest demonstrations of a theory speaking confidently across centuries. Even the tides that rose and fell on Earth found a clear explanation in the combined gravitational influence of the Moon and the Sun, each pulling gently on the oceans and shaping the daily rhythm of shorelines. One of the most dramatic validations arrived in the 19th century. Careful astronomers noticed that Uranus was not moving exactly where Newtonian predictions said it should. Tiny deviations lingered, too small to dismiss, yet too persistent to ignore. Instead of doubting Newton's equations, scientists asked whether another unseen planet might be tugging on Uranus. Through pure mathematics and nothing more, they calculated where such a world would have to be for its gravitational pull to explain the discrepancies. When telescopes turned to that patch of sky, they found Neptune almost exactly where calculations predicted. It was a triumph so complete that many believed Newton's law had reached perfection. A force that could reveal new planets before they were seen seemed beyond challenge. Yet beneath this triumph lay questions that never entirely faded. Newton himself admitted that he did not know how gravity acted across empty space. His equations described what happened but did not offer a mechanism. How could one mass influence another without contact? The idea of action at a distance troubled many thinkers well into the Victorian era. As physics advanced through the 19th century, the mystery deepened. James Clerk Maxwell unified electricity and magnetism into a theory that demanded signals travel at a finite speed, the speed of light. But Newtonian gravity appeared to act instantly across any distance. If the sun were suddenly displaced, Newtonian theory suggested Earth would feel the change immediately, even though light itself would need several minutes to arrive. This tension was subtle but real, and physicists recognized that a complete picture of nature should not allow contradictory behaviors. Astronomers also discovered small irregularities within the solar system that refused to fit neatly into Newton's predictions. Mercury, the smallest inner planet, traced an orbit whose closest point to the Sun slowly shifted over time. Most of this shifting matched Newtonian expectations, caused by gravitational tugs from other planets, yet a small residue remained unexplained. Though the discrepancy was tiny, it signaled that something in the theory or its application had reached a limit. Physicists of the era proposed many possibilities, from unseen matter to slight imperfections in the Sun's shape, but no explanation fully resolved the question. Still, the Victorian world greeted these issues with calm confidence. After all, Newtonian gravity had guided sea navigation, planetary prediction, and telescope design for generations. The law seemed so reliable that many believed the universe operated like a grand machine, whose rules were already written. Even apparent anomalies were expected to yield eventually to more careful measurement. Gravity, according to this view, was complete. But in the background, a quiet awareness grew. The more precisely scientists examined the heavens, the more hints they found that Newton's elegant law might not be the final story. Tiny, unexplained motions and theoretical tensions suggested that space itself might be hiding a deeper truth. The stage was set for a transformation, one that would emerge not from altering Newton's equations, but from reimagining the very fabric in which those equations lived. The quiet pressure building beneath 19th century astronomy did not erupt all at once. Instead, it unfolded like a slow tightening of threads, each observation adding tension to a fabric that everyone assumed was solid. As telescopes improved and star charts grew more precise, the heavens revealed details that earlier generations could never have detected. Every small deviation from Newtonian prediction became a point of interest. Astronomers, who once celebrated the clean geometric elegance of orbital paths, found themselves confronted with motions that were slightly imperfect, slightly misaligned, slightly resistant to the old explanations. None of these discrepancies on its own challenged the foundations of Newton's universe, but together they hinted that something deeper waited beneath the surface. Mercury's orbit remained the most persistent of these hints. Each time the planet swung closest to the Sun, its position drifted by an amount that had been measured, remeasured, and confirmed across generations. The discrepancy was small enough that a casual observer would never notice it, yet large enough to trouble minds devoted to precision. Many proposed that an unseen planet might exist even closer to the Sun, exerting a subtle gravitational pull that could account for the wandering orbit. This hypothetical world, named Vulcan, became a subject of extensive searching. Astronomers scanned the blinding region near the solar disk during eclipses and through specialized instrumentation, convinced that discovery was only a matter of time. Yet year after year, no such planet appeared. With each non-detection, the puzzle grew more pronounced. The mysteries were not confined to planetary motion. As physicists studied light and electricity, they uncovered laws that suggested the universe operated with deeper constraints than previously imagined. Maxwell's equations showed that electromagnetic waves traveled through space at a fixed finite speed. This limit was not optional, but built into the structure of electricity and magnetism themselves. If gravity acted instantaneously across the cosmos, while electromagnetic signals obeyed a strict speed limit, the two great frameworks of 19th century physics stood in quiet contradiction. The universe, so harmonious in the Newtonian picture, now displayed two different ways of sending influence from place to place. Many believed a substance called the ether filled all of space and carried light waves through its medium. If such a substance existed, perhaps gravity acted through it as well. Yet the ether itself remained elusive, unmeasured and unconfirmed. As the century closed, scientists built careful experiments to test the nature of this ether. The Michelson-Morley experiment attempted to detect Earth's motion through such a medium by comparing the speed of light in different directions. If Earth moved through an ether wind, light would reveal that motion. The result was a null finding. No matter the direction, light traveled at the same speed. This discovery shocked many because it undermined the idea of a stationary ether and deepened the tension between Newtonian gravity and the emerging understanding of electromagnetic behavior. The reliable coherence of the Newtonian world began to seem less absolute, although no one yet knew what would replace it. In this period of uncertainty, a new conceptual landscape was forming. Lorentz transformations, developed to reconcile Maxwell's equations with the null results of ether experiments, revealed that space and time might not be rigid backgrounds after all. Instead, they could shift according to motion, preserving the speed of light but altering intervals of length and duration. These ideas were mathematically compelling, yet physically unsettling. They suggested that the arena in which all forces acted was more fluid than previously believed. Still, most scientists treated these transformations as clever mathematical tools designed to preserve Maxwell's equations rather than signs of a new reality. Amid this shifting ground, Newton's law continued to dominate practical astronomy. Planetary tables relied on it, naval expeditions used it, and engineers trusted it when designing instruments. The theory worked so well that even when faced with conceptual puzzles, many assumed the core idea remained unshakable. Nature seemed too orderly for such a successful law to be fundamentally incomplete. Yet the clues remained. Mercury continued to defy full explanation. The nature of instantaneous gravitational influence remained unresolved. The conflict between Newtonian gravity and the finite speed of electromagnetic waves grew sharper as new experiments confirmed the consistency of light's behavior. The 19th century scientific world lived in a strange balance. On one side stood the immense success of Newton's gravitational force, a pillar that had guided humanity for more than 2 centuries. On the other side grew a quiet but undeniable awareness that something essential was missing. These concerns did not undermine the practical power of Newtonian mechanics, but they whispered of a deeper order waiting to be discovered. Many felt that the next breakthrough would refine Newton's work rather than replace it. Few imagined that the very concept of force might be reframed. Even fewer suspected that space and time themselves might shift from passive backgrounds to active participants in the unfolding of motion. The universe was preparing to reveal that gravity was not a force reaching across empty space, but a consequence of the shape of space itself. The questions that accumulated across the 19th century were not obstacles to Newtonian mechanics, but invitations to a new understanding, and soon a young thinker would step into this landscape and see what others had not yet considered. He would not begin by challenging the laws of force, but by questioning what space and time actually were. The turning of the 20th century carried with it a sense that the universe was almost fully understood, yet a quiet unease lingered beneath that confidence. Scientists sensed that the remaining mysteries were not random imperfections, but signs of something more profound. The old assumption that space and time were simple, absolute, and unchanging backdrops began to feel increasingly fragile. The unresolved puzzles of the 19th century pressed against the limits of Newton's world and hinted that the foundations themselves might require rethinking. Into this atmosphere stepped a young patent clerk who approached physics with a mixture of curiosity and independence that allowed him to see what many others overlooked. He did not begin by questioning gravity. Instead, he asked a more fundamental question. What is the nature of space and time? Einstein's early reflections focused on light, clocks, and the strange consistency revealed by experiments that failed to detect Earth's motion through any ether. He imagined what it would mean to ride alongside a beam of light and realized that the traditional understanding of time could not survive such a thought. If light always traveled at the same speed for every observer, then time itself had to stretch or compress, depending on motion. The implications were astonishing. Lengths could change, durations could shift. Events that seemed simultaneous to one observer could unfold in different order for another. The universe did not offer a single fixed framework in which all motion occurred. Instead, it provided a flexible structure that adjusted depending on the observer. Even before these ideas matured into the full expression of special relativity, they carried consequences that reached far beyond the physics of electromagnetism. If space and time were not rigid backgrounds, then Newton's description of gravity as an instantaneous force acting across that background was placed under new pressure. The contradictions that had troubled physicists for decades no longer seemed like isolated difficulties, but parts of a larger puzzle. How could a force operate instantaneously in a universe where signals were constrained by the speed of light? How could the geometry of the cosmos remain fixed if physical laws required transformations that blended space and time together. The very stage on which Newtonian gravity played its role appeared to be shifting. Yet while these new insights illuminated the limitations of Newton's framework, they did not diminish its achievements. Newton's equations continued to guide spacecraft and predict planetary motion with extraordinary accuracy. They remained essential tools that spoke effectively in most situations. But a theory can be successful and still incomplete. Einstein came to believe that the limitations were not mistakes in Newton's reasoning, but consequences of building a theory of gravity on a stage that itself needed to be reimagined. Instead of modifying the force, he sought a new understanding of the arena where motion unfolded. As new ideas emerged, scientists returned to the old puzzles and found that they resonated with fresh meaning. Mercury's tiny orbital drift, once a stubborn anomaly, became a clue that gravity might involve more than a simple inverse square force. The tension between instantaneous gravitational influence and the finite speed of electromagnetic signals pointed toward a deeper unity between all physical interactions. The subtle failures of the ether model, instead of proving inconvenient, hinted that the background of the universe was not a substance-filling space, but space itself, behaving in a previously unrecognized way. The 19th century understanding of gravity reached a limit, not because Newton was wrong, but because the conceptual framework surrounding his ideas had aged. A new century called for a new perspective, one that would respect the successes of classical mechanics while opening a path toward a richer understanding. Many physicists recognized that progress required a theory that did not rely on instantaneous action across emptiness. But few had the courage to question the nature of space and time themselves. Einstein prepared to take that step, guided not by speculation, but by a commitment to follow the consequences of empirical evidence wherever they led. The stage was ready. The old world of forces, rigid space, and absolute time had carried science far, yet its foundations trembled under the weight of new discoveries. What began as small irregularities in planetary motion and subtle inconsistencies in theoretical expectations evolved into a profound question. What if gravity was not a force at all? What if the universe shaped motion not through invisible pulls, but through the very geometry of space and time? With these questions forming at the edge of scientific understanding, Einstein was poised to reshape the foundations of physics. The next steps would reveal that the cosmos was far stranger and more elegant than the Newtonian picture had ever allowed. Motion across the universe would soon be understood not as the result of forces acting across distance, but as the natural consequence of following paths through a curved and dynamic space-time. In the quiet pre-dawn hours of the mid-19th century, observatories across Europe and beyond turned their attention toward a small and elusive world that circled the sun with a swiftness unmatched by any other planet. Mercury, glowing faintly against the solar glare, had long been an object of fascination. Its path was traced with growing precision as telescopes improved and astronomers refined their instruments. Yet as they compared their observations with the predictions calculated through Newton's trusted laws, a tension emerged that refused to disappear. Mercury's orbit did not behave exactly as expected. Its point of closest approach to the Sun, the perihelion, drifted in a slow and steady motion that could not be fully explained by the gravitational tugs of the known planets. This drift, measured repeatedly across generations, remained one of the most enduring anomalies of classical astronomy. The history of this puzzle began in earnest, with the careful observations of Urbain Le Verrier, a mathematician whose sharp analytical mind had already guided astronomers to the discovery of Neptune. When he turned his attention to Mercury, he approached the problem with the same confidence that the inverse square law would reveal all hidden influences. He calculated the gravitational effects of Venus, Earth, Jupiter, and the other planets, combining them with the contributions of Newtonian theory. Most of the observed drift was accounted for, but a small extra rotation remained. This residue was not noise. It was persistent, measurable, and stubbornly resistant to interpretation. In a period when Newton's gravitational force was seen as nearly flawless, such a discrepancy demanded a cause. The natural explanation seemed to be another planet, one closer to the Sun than Mercury, hidden within the blinding glare that made observation nearly impossible. Leverrier named this hypothetical world Vulcan. If it existed, its gravitational pull could neatly account for the extra motion. Astronomers searched with determination, especially during total solar eclipses, when the sun's overwhelming brightness momentarily dimmed. Claims appeared from time to time, reports of dark spots or faint objects glimpsed near the solar disk, yet none withstood the scrutiny of repeated observation. Each new claim invited renewed excitement, followed inevitably by disappointment as follow-up attempts failed to confirm it. The longer Vulcan remained unseen, the more troubling Mercury's anomaly became. While the search for Vulcan occupied much of the astronomical community, another profound puzzle was unfolding in a different domain of physics. Light, electricity, and magnetism had been unified through the work of Maxwell into a beautiful system of equations that predicted a finite and universal speed for electromagnetic waves. This speed, the speed of light, did not depend on the motion of the source or the motion of the observer. It was a fixed feature of the natural world. But Newtonian gravity, in its classical form, acted with instantaneous influence across any distance. If the Sun were to shift in position, Earth would feel the change in its gravitational pull immediately according to Newton's law. This stood in sharp conflict with the principle that no physical influence could exceed the speed of light. Physicists of the time tried to reconcile these ideas through the concept of the ether, an invisible medium thought to fill all of space and carry light waves through it. If Earth moved through this medium, the speed of light should differ depending on its direction of travel. The Michelson-Morley experiment was designed to detect that difference with unparalleled precision. Their apparatus used beams of light traveling along perpendicular paths, expecting to find slight variations in travel time caused by Earth's motion through the ether. The result was startling. No difference appeared. Light traveled at the same speed in every direction, regardless of Earth's motion. This null result challenged the very existence of the ether and deepened the contradiction between Newtonian gravity and electromagnetic theory. Mathematicians attempting to preserve the integrity of Maxwell's equations introduced transformations that allowed time and space to shift in ways that kept the speed of light constant. Lorentz transformations demonstrated that moving clocks would slow and moving lengths would contract, not as illusions, but as fundamental properties required by the laws of electromagnetism. These transformations were powerful mathematical tools, yet few at the time believed they described physical reality. Instead, they were seen as adjustments needed to preserve equations whose deeper meaning remained uncertain. Through all of these developments, the Newtonian worldview retained immense authority. Navigators trusted it, astronomers depended on it, engineers built instruments around it. A small planetary discrepancy or a puzzling optical experiment could not easily shake centuries of success. Yet the cracks were no longer isolated. They formed a pattern, a quiet suggestion that the universe might not be as rigid or as simple as once believed. Mercury's orbit whispered that gravity might not follow Newtonian expectations. The behavior of light insisted that space and time might not be absolute. The failure to detect an ether hinted that the very medium of the cosmos might have been misunderstood. These clues were scattered, disconnected, and often treated as annoyances rather than signposts. But together, they formed the outline of a deeper problem. Something fundamental within the classical picture no longer fit. The universe was consistent, but the theories that described it were not. The stage was set for a transformation that would soon show that the issue was not Newton's mathematics, but the assumptions about the world in which that mathematics was being applied. The years that followed, the Michelson-Morley result revealed a growing tension that no simple adjustment could resolve. Physicists understood that something profound was unfolding, yet no one knew which thread to follow. Some insisted that new experimental errors would emerge and restore confidence in the ether. Others argued that the ether might possess strange elastic or dynamic properties that had not yet been imagined. But a small group sensed that the problem ran deeper. The issues in the behavior of light and the irregularities in Mercury's orbit were not isolated flaws. They pointed toward a single missing idea, something that touched the very foundation of how motion was described. By the late 19th century, more careful measurements confirmed that Mercury's perihelion drift remained stubbornly stable. The tiny angle, measured in arc-seconds per century, seemed insignificant in ordinary perception, yet it was recorded with instruments that had grown increasingly precise. Astronomers compared older observations with newer ones, refining planetary masses, recalculating perturbations, and adjusting for every known influence. The result never changed. The unexplained extra motion remained. It was neither random nor fading. It was a quiet signal from the inner solar system, telling astronomers that gravity behaved in some slightly different way near the intense mass and proximity of the Sun. The persistence of this puzzle fueled further attempts to salvage the Newtonian picture. Some proposed that the Sun was not a perfect sphere, but slightly flattened. If the Sun bulged at the equator, its gravitational field would deviate from perfectly spherical symmetry and could in theory produce the needed effect. Observations of solar shape were gathered, re-examined, and compared with models. The required deformation proved far greater than what the data allowed. The Sun appeared too round, its shape too close to perfection, to account for the anomaly. This explanation, like Vulcan before it, faded into uncertainty. As the 19th century approached its final decades, the new transformations derived by Lorentz and others began to reveal a deeper structure within the laws of physics. These transformations preserved the speed of light for all observers, something that the ether model could not achieve. They suggested that time itself must stretch or compress depending on motion, and that space must adjust to preserve the same universal limit. At first, these ideas were interpreted as mere mathematical corrections, clever but not physically real. Yet the more scientists studied them, the harder it became to treat them as superficial. These transformations were not patches, they were hints of a new architecture underlying the universe. Still, the conceptual shift remained incomplete. No one had yet linked this emerging structure of space and time with the problems facing Newtonian gravity. It was one thing to adjust clocks and rulers for electromagnetic behavior. It was another to let those adjustments influence the interpretation of motion across the solar system. The idea that gravity itself might require rethinking was not yet widely entertained. For most physicists, Newton's law was far too successful to question. It described the tides. It guided planetary motion with astonishing accuracy. It revealed Neptune before anyone had seen it. A theory with such reach did not seem vulnerable, but nature does not yield to reputation. The stubborn discrepancy in Mercury's orbit remained untouched by all attempts to explain it. The tension between instantaneous gravitational action and the finite speed of light sharpened each year as more experiments confirmed the constant speed of electromagnetic waves. The Lorentz transformations, originally presented as mathematical tools, proved too consistent and too elegant to dismiss. They implied that space and time were not passive containers, but flexible quantities shaped by motion. The classical framework that supported Newtonian gravity felt increasingly strained, as though it carried more weight than it was meant to bear. At the same time, experimentalists continued to examine the behavior of light with greater precision. Each new test reaffirmed the universal speed predicted by Maxwell's equations. The absence of any detectable ether wind in repeated experiments grew impossible to ignore. The world seemed to operate according to principles that did not fit the assumptions of classical mechanics. Motion was relative. Time was not absolute. The structure of space was more subtle than the rigid stage Newton had imagined. For the first time, scientists began to consider that the classical picture might require more than small corrections. Perhaps the old framework, for all its successes, was incomplete in a deeper sense. The universe was sending signals through Mercury's orbit, through the behavior of light, and through the failures of the ether concept. These signals pointed toward a missing idea, something that unified motion, time, and propagation of influence in a way that classical mechanics did not capture. In these final years before the arrival of a new perspective, the scientific community found itself standing on the edge of a conceptual shift. They had the tools to see the problem. They had the data. They had the mathematics. Yet the decisive insight had not yet been made. The world awaited someone who would look at these scattered clues and recognize that the issue was not merely with Newton's force law, but with the nature of the stage on which all forces acted. It awaited someone who would realize that the universe could not be understood fully without reconsidering what space and time truly were. The final years before the new century carried a strange duality. On one side stood a physics that seemed complete. On the other stood a growing set of clues that quietly refused to fit. Scientists lived in a world where calculations guided ships across oceans, where predictions of eclipses matched reality to astonishing precision, and where mechanical laws appeared strong enough to hold the entire universe in place. Yet beneath this triumphant surface lay the unmistakable feeling that something fundamental had been overlooked. The world behaved with more subtlety than the equations suggested. The cracks showed themselves only in the most delicate measurements, but they showed themselves consistently, and careful minds could not ignore them. Mercury's stubborn orbital drift remained the clearest whisper of this deeper truth. Year after year, astronomers added new observations, correcting for every influence they could imagine. They accounted for the pull of Venus, Earth, and Jupiter. They adjusted for small motions of the Sun itself. They improved their models of planetary interactions. And still, the anomaly remained. It was as if nature had tucked a message inside the orbit of the smallest planet. A message too faint for earlier generations to hear, but impossible for modern precision to conceal. Each failed explanation tightened the focus of the scientific community, narrowing the possibilities and preparing the ground for a more radical idea. Meanwhile, the study of light continued to challenge the classical worldview. Experiments that once might have been dismissed as curiosities grew into pillars of evidence. The speed of light remained unshaken by any attempt to alter it through motion of the observer or the source. Whether measured on Earth, reflected from distant mirrors, or observed in astronomical phenomena, it stood as an unyielding constant. This consistency forced physicists to rethink assumptions that had been taken for granted for centuries. If no influence involving electromagnetic waves could exceed this speed, then instantaneous action at a distance became more than a philosophical discomfort. It became a physical impossibility. The concept of the ether, once a reassuring solution to many puzzles, weakened under the weight of evidence. Scientists had envisioned it as a universal medium through which light waves traveled, filling all space with a gentle but undetectable substance. But as experiments grew more refined, the ether remained stubbornly absent. The absence was not casual. It was systematic. No matter how the tests were arranged, no motion through an ether wind appeared. The world behaved as though such a medium did not exist, as though light required no carrier at all. This absence puzzled physicists because it left an unsettling question. If no ether filled the universe, then what exactly was space? Was it a true vacuum, empty and inactive? Or could its properties be more intricate than previously believed? Could the fabric of the cosmos itself play a role in shaping the behavior of light, matter, and motion? These questions, once peripheral, began to move closer to the center of scientific thought. The Lorentz transformations, which preserved the speed of light through mathematical adjustments to time and distance, added to the mystery. At first, they were treated as clever inventions designed to patch a theory that resisted conventional understanding. But the transformations possessed a coherence that hinted at something deeper. They revealed that the measurement of time depended on motion, and that the measurement of distance depended on speed. These were not mere mathematical conveniences. They were the fingerprints of a world whose structure differed from the classical picture in fundamental ways. Still, many scientists remained cautious. The transformations did not by themselves explain gravity. They did not resolve Mercury's orbit. They did not unify classical mechanics with electromagnetism. They were fragments of a larger pattern, waiting for someone to assemble them into a coherent whole. The stage was set, the pieces arranged, yet the decisive insight remained unspoken. The scientific community had come close to recognizing the need for a dramatic shift, but stopped short of crossing that boundary. The old assumptions still held too strongly, reinforced by centuries of success. In this moment of quiet tension, the world awaited a new perspective, one capable of connecting these scattered puzzles. The resolution would not come from adding new forces or inventing unseen planets. It would come from questioning the very nature of the framework in which all motion occurred. The idea that gravity might not be a force at all lingered just beyond the edge of accepted thought, unspoken yet increasingly necessary. The universe had provided clues through every precise measurement, through every stubborn anomaly, through every experiment that refused to align with classical expectations. Someone needed only to follow those clues to their logical conclusion. That step would soon be taken, not by expanding Newton's law, but by reimagining the meaning of motion itself. The transformation was close, waiting for a mind willing to see that the solution to Mercury's orbit, the behavior of light, and the absence of ether were all expressions of a deeper truth. The universe did not merely contain space and time, it shaped them, and in turn, they shaped the motion of every object within them. At the dawn of the 20th century, a quiet conceptual revolution began to gather strength, not through dramatic announcements or sweeping claims, but through the steady accumulation of evidence that the old framework of physics could no longer hold. Into this landscape stepped a young Albert Einstein, working in the Swiss patent office and thinking with a freedom that the academic world rarely afforded. His mind wandered across the boundaries of electromagnetism, mechanics, and geometry, searching for a single consistent picture that could accommodate all the clues the 19th century had left unresolved. He did not attempt to repair Newtonian gravity or invent new forces. Instead, he began by questioning the structure that all theories assumed without hesitation. He asked what space and time truly were. Einstein knew that the speed of light, revealed through both Maxwell's equations and meticulous experiment, appeared to be the same for every observer regardless of motion. This fact was more than a mathematical detail. It contradicted the common-sense idea that velocities should add. If a train moved rapidly and a beam of light shone from its front, classical reasoning suggested that an outside observer should measure the light as traveling faster than its usual speed. Yet nature refused to behave this way. No matter how one moved, the speed of light remained unchanged. Einstein approached this fact not as an annoyance to be explained away, but as a fundamental truth that demanded a new description of reality. If the speed of light was constant for all observers, then the structure of time and distance had to adjust to preserve that constancy. He considered thought experiments with a clarity that allowed him to see consequences in simple, visual terms. If two lightning bolts struck opposite ends of a moving train and a person standing beside the tracks saw them simultaneously, someone riding inside the train would not. The motion of the train would carry them closer to one flash and farther from the other. Although the light from both strikes would reach the standing observer at the same moment, the traveling observer would receive one signal first and the other later. The conclusion was unavoidable. Simultaneity was not universal. Two events that appeared to occur at the same moment for one observer might unfold in different order for another. This was not a trick of perception. It was a physical feature of the universe. From this simple realization, Einstein followed the logic step by step. If simultaneous events could differ between observers, then time itself could not be absolute. Time must stretch or contract depending on motion. The same reasoning applied to distances. If the time taken for light to travel a fixed path was the same for all observers, then lengths must change in order to maintain that constancy. These were not adjustments imposed by measurement error. They were the natural geometry of a world in which the speed of light was a fundamental limit. The result became known as time dilation and length contraction, consequences of special relativity. At the dawn of the 20th century, a quiet conceptual revolution began to gather strength, not through dramatic announcements or sweeping claims, but through the steady accumulation of evidence that the old framework of physics could no longer hold. Into this landscape stepped a young Albert Einstein, working in the Swiss patent office and thinking with a freedom that the academic world rarely afforded. His mind wandered across the boundaries of electromagnetism, mechanics, and geometry, searching for a single consistent picture that could accommodate all the clues the 19th century had left unresolved. He did not attempt to repair Newtonian gravity or invent new forces. Instead, he began by questioning the structure that all theories assumed without hesitation. He asked what space and time truly were. Einstein knew that the speed of light, revealed through both Maxwell's equations and meticulous experiment, appeared to be the same for every observer regardless of motion. This fact was more than a mathematical detail. It contradicted the common-sense idea that velocities should add. If a train moved rapidly and a beam of light shone from its front, classical reasoning suggested that an outside observer should measure the light as traveling faster than its usual speed. Yet nature refused to behave this way. No matter how one moved, the speed of light remained unchanged. Einstein approached this fact not as an annoyance to be explained away, but as a fundamental truth that demanded a new description of reality. If the speed of light was constant for all observers, then the structure of time and distance had to adjust to preserve that constancy. He considered thought experiments with a clarity that allowed him to see consequences in simple, visual terms. If two lightning bolts struck opposite ends of a moving train and a person standing beside the tracks saw them simultaneously, someone riding inside the train would not. The motion of the train would carry them closer to one flash and farther from the other. Although the light from both strikes would reach the standing observer at the same moment, the traveling observer would receive one signal first and the other later. The conclusion was unavoidable. Simultaneity was not universal. Two events that appeared to occur at the same moment for one observer might unfold in different order for another. This was not a trick of perception. It was a physical feature of the universe. From this simple realization, Einstein followed the logic step by step. If simultaneous events could differ between observers, then time itself could not be absolute. Time must stretch or contract depending on motion. The same reasoning applied to distances. If the time taken for light to travel a fixed path was the same for all observers, then lengths must change in order to maintain that constancy. These were not adjustments imposed by measurement error. They were the natural geometry of a world in which the speed of light was a fundamental limit. The result became known as time dilation and length contraction, consequences of special relativity that have since been confirmed in countless experiments. Moving clocks do run slower. Moving rulers do contract along the direction of motion. High-energy particles created in the upper atmosphere survive to reach Earth's surface because their internal clocks run more slowly in their rapid flight. These effects are measurable, repeatable, and essential to modern technology, ranging from particle accelerators to satellite timing systems. Einstein's insight reached even farther. The classical separation between space and time could no longer survive. The universe did not provide them as independent arenas. Instead, they blended into a single four-dimensional fabric known as spacetime. Hermann Minkowski later gave this idea precise mathematical form, showing that space and time are woven together through a structure in which intervals depend on the motion of the observer. In this formulation, objects move not through separate space and separate time, but through a unified continuum. Straight line paths in this continuum correspond to inertial motion. motion that requires no force to sustain it. An object traveling freely, unpushed and unpulled, follows the simplest possible path through space-time. This reinterpreted inertia, not as a mysterious resistance to change, but as a geometric property of trajectories. The implications were profound. In the classical world, forces determined motion. In the relativistic world, motion was a natural consequence of geometry, unless something acted to deviate it. Einstein realized that this geometric structure must apply to every physical phenomenon, including gravity. Yet gravity, as Newton described it, was a force acting instantaneously at a distance, incompatible with the new understanding of space-time. Special relativity left no room for instantaneous influence. All signals, all interactions, all causal effects must propagate no faster than the speed of light. Einstein recognized that if gravity was to be reconciled with special relativity, the old picture of a force transmitting across empty space had to be replaced. The solution could not be an adjustment to the force law. It had to be a reformulation of gravity itself. The question was not how masses reached across distance to pull one another. The question became how space-time behaved in the presence of matter and energy, and how objects moved when space-time itself was no longer rigid. Special relativity did not solve the problem of gravity, but it made it impossible to ignore. It reshaped the stage on which all physics occurred. It showed that space and time were dynamic actors, capable of shifting according to motion and incapable of supporting instantaneous interactions. It narrowed the possibilities for any future theory. Whatever gravity truly was, it would have to fit within a universe where the structure of space-time mattered, as much as the objects that moved through it. The path forward was now illuminated. Einstein had transformed the way motion was understood, replacing unquestioned assumptions with a framework grounded in experiment and logical necessity. But the greatest transformation still lay ahead. If the geometry of space-time shaped motion, then perhaps gravity itself was not a force, but a manifestation of that geometry. Einstein's new understanding of space and time did more than untangle the contradictions that had troubled 19th century physics. It opened a doorway into a deeper vision of the universe, a vision in which motion was no longer something imposed by forces alone, but a natural unfolding within space-time itself. With the speed of light fixed as an unbreakable limit, every observer carried a personal weaving of distances and durations that shaped how they perceived events. Time dilation and length contraction were not distortions layered onto reality. They were expressions of the geometry that governed all motion. This geometry, quiet yet powerful, became the stage where the next great transformation would occur. As special relativity settled into the scientific world, physicists realized that the theory did more than redescribe motion. It provided strict rules for what any future theory must respect. The first rule was causality. No influence could travel faster than the speed of light. The second was the relativity of simultaneity. Different observers could legitimately disagree on the order of events without violating any physical principle. The third was the unity of space and time, which demanded that all physical laws remain consistent under the transformations that connected one observer to another. These were not optional refinements. They were structural necessities. Any theory that ignored them would contradict decades of experimental evidence. In this new picture, an object that moved freely through space without any external influence did not require a force to keep going. It simply followed the straightest possible line through space-time, a path determined by the geometric structure around it. This perspective transformed the very concept of inertia. Instead of viewing inertia as an object's natural resistance to changes in motion, it became the recognition that objects naturally trace geodesics in space-time unless something compels them otherwise. Forces were no longer the primary explanation for motion. They became explanations for deviations from motion. Einstein understood that this principle had profound implications for gravity. If objects followed straight paths through space-time when no forces acted, then gravity's ability to curve those paths could not be explained by a traditional force pushing or pulling. Something deeper must be at work. The universe seemed to be revealing that motion depended on the shape of space-time itself. To describe gravity within this new framework, one had to understand how matter might alter. That shape, how mass and energy could influence the geometry that guided all trajectories. Special relativity raised the question but did not answer it. For all its power, the theory applied only to scenarios where the geometry of space-time remained flat and uncurved. It worked flawlessly for high-speed motion, electromagnetic interactions, and the behavior of clocks and rulers in uniform motion. But it offered no mechanism by which gravity could arise. It described a universe without curvature, a universe that could not yet explain Mercury's orbit, or the bending of starlight, or the slow drift of time near massive bodies. The missing piece was not a new force law. It was a new understanding of geometry. Einstein began to suspect that the classical view of space as a rigid emptiness was incorrect. The clues were scattered but compelling. The constancy of the speed of light suggested that space-time had built-in rules. The failure of the ether implied that space was not a passive medium, but an entity whose properties were intrinsic. The inability of Newtonian gravity to operate within the constraints of relativity suggested that instantaneous action at a distance was impossible. All of these ideas converged toward a single insight. If space and time were not rigid, perhaps they could bend. This was not an easy thought to accept. The idea that the very fabric of the universe might curve required a radical break from centuries of intuition. Yet Einstein was not guided by abstraction. He followed the consequences of experiment. If objects moved along straight lines in flat space-time, yet curved their trajectories in the presence of gravity, perhaps they were still following straight lines, but within a curved space-time. A planet orbiting the Sun might not be pulled in the classical sense. It might be tracing the natural geodesic of a bent geometry shaped by the Sun's mass. To explore this possibility, Einstein sought mathematical tools that could describe curved spaces. He found them in the work of Riemann and others who had developed a language for expressing curvature in higher dimensional structures. Although these mathematical ideas were originally created to explore abstract surfaces, they offered a way to express a physical truth that no one had previously considered. If mass and energy changed the geometry of space-time, then the motion of objects near them could be understood as natural motion through a curved landscape. No force would be needed. Geometry alone would guide the paths. Einstein sensed that this approach could unify the clues left unresolved by classical mechanics. The bending of light could become a natural consequence of space-time curvature. The extra drift in Mercury's orbit could arise from motion near the intensely curved region close to the Sun. The conflict between instantaneous action and the finite speed of light could vanish if gravity were not a transmitted force at all, but a geometric response that propagated through space-time in accordance with relativistic rules. The steps toward this new theory were gradual, marked by deep reflection and a willingness to abandon assumptions that had guided thinkers for generations. Einstein knew that special relativity was a foundation, but not the destination. It clarified the rules, yet left the central mystery unresolved. The quest to understand gravity had now become the quest to understand how space-time itself behaved. The stage was prepared for the next leap. Special relativity had rewritten space and time. The next discovery would reveal that gravity was not a force acting within space-time, but the curvature of space-time itself. Einstein's growing conviction that gravity must emerge from the geometry of space-time did not arrive in a single moment of revelation. It formed slowly, shaped by countless reflections on problems that classical physics had never resolved. He understood that special relativity had placed strict limits on how the universe could behave. Signals could not travel faster than light. Simultaneity could shift between observers. Distances and durations were not absolute. These principles were not decorative. They were woven into the structure of reality. Any explanation of gravity that ignored them would contradict the most reliable experiments ever performed. The old picture of an instantaneous force acting across empty space no longer belonged to the physical world revealed by evidence. Einstein began to think of space-time as a vast landscape whose shape determined how objects moved. In a flat landscape, the straightest paths are familiar and intuitive. But on a curved surface, the natural paths bend even without any applied force. A sphere offers the simplest demonstration. A traveler walking steadily across its surface and following what feels like a straight line inevitably moves along a curved track. It is not an external influence that bends the path. It is the geometry itself. Einstein asked whether the same principle could apply to gravity. What if planets moved along curved trajectories, not because they were pulled, but because space-time near the Sun was bent? The elegance of this idea was impossible to ignore. It offered a geometric explanation for motion that preserved the principles of relativity and required no instantaneous interaction. But imagining curved space-time was not enough. Einstein needed a mathematical structure capable of expressing how mass and energy could influence geometry. He explored earlier works that had developed the language of curved surfaces. Riemann had created a framework for describing distance, curvature, and geodesics on surfaces that defied classical intuition. Ricci and Levi-Civita had refined this language into a set of tools that could express curvature in more general and complex spaces. Although these mathematicians had pursued their work for reasons unrelated to physics, their ideas provided exactly the foundation Einstein needed. Slowly and carefully, he began to adapt these mathematical concepts to the physical world, shaping them into a structure that could describe a dynamic space-time. His intuition told him that the key lay not in inventing new forces, but in understanding how geometry responded to mass. If a massive object like the Sun distorted the space-time around it, then planets would follow curved paths naturally, much as a marble rolling across a bent surface follows whatever contour lies beneath it. The greater the mass, the more pronounced the curvature. The closer an object came to the source of that curvature, the more sharply its path bent. This idea carried immediate consequences for the puzzles that had plagued astronomers. The unexplained drift in Mercury's orbit might not be a defect in Newton's law, but a sign that Newton had assumed a flat geometry where the universe provided a curve. Einstein's search for a new understanding of gravity did not begin with exotic mathematics or distant cosmic imagery. It began with a moment of simple clarity, a moment he later described as the happiest thought of his life. He imagined a person falling freely from the roof of a house. During the fall, that person would feel weightless. Any object released beside them would float as though gravity had vanished. Inside that moment of descent, the pull of the earth would no longer announce itself. The falling person would drift in a calm suspension, as though space itself had softened. This thought carried a truth that classical physics had never recognized. The experience of falling erased gravity, not by removing the mass of the earth, but by placing the observer in a state where the effects of gravitational pull disappeared. Einstein realized that this was no mere coincidence, it was a profound clue. He understood that if an observer in free fall felt no gravitational force, then gravity might not be a true force at all. It might be something that could vanish under the right conditions, something that revealed itself only when motion deviated from natural paths. To explore this idea, he imagined elevators, spacecraft, and sealed chambers drifting through space. A person inside an accelerating chamber would feel a force pressing them to the floor. They would feel weight, yet no planet would need to be nearby. The feeling would arise entirely from acceleration. Einstein recognized a remarkable symmetry. Acceleration could imitate gravity with perfect fidelity. If acceleration could create the illusion of gravitational force, then gravitational force might be the illusion, and acceleration the real phenomenon. This insight became the equivalence principle. It stated that the effects of gravity and the effects of acceleration were locally indistinguishable. No experiment performed within a small enclosed space could reveal whether the force felt underfoot came from standing on Earth or from rising upward in an accelerating elevator far from any planet. The principle was simple to state, yet transformative in meaning. It suggested that gravity might be a property of motion rather than a pull from a distant mass. It hinted that the universe might conceal a geometric truth behind the sensations of weight and fall. If standing still on Earth felt identical to accelerating upward in empty space, then perhaps standing still on Earth was not true rest at all. Perhaps it was a state of forced deviation from a natural path that space-time had already traced. Einstein tested this idea through ever more subtle thoughts. He considered how light behaved in an accelerating room. A beam entering through one wall would strike the opposite wall at a lower point because the room would rise during its travel. If acceleration bent the path of light, then gravity should do the same. This prediction was not an abstraction. It was a concrete, testable statement about the real world. Light passing near a massive body should curve, not because it interacted with a force, but because space-time near mass shaped the natural trajectory of all things, including light itself. This insight tied gravity to a universal effect, one experienced by matter and radiation alike. It moved Einstein closer to the idea that curvature, not force, governed motion. The equivalence principle gained further strength from experimental findings that had been quietly accumulating. Torsion balance measurements performed by Laurent et Eötvös, and later refined by others, showed that inertial mass and gravitational mass were equal to an extraordinary degree. Objects of different composition, when released in the same gravitational field, accelerated at precisely the same rate. This equality was not a coincidence. It reflected a deep property of nature that had long been noticed but never fully explained. In Newtonian mechanics, this equivalence was simply assumed. In Einstein's hands, it became evidence that gravity might arise from geometry rather than from a true physical force. If all objects, regardless of their makeup, followed the same trajectories in a gravitational field, then those trajectories must be determined by something universal. The geometry of space-time offered such universality. Einstein explored these ideas with growing confidence. He saw that the equivalence principle provided a bridge between special relativity and a deeper theory of gravity. It allowed him to extend the geometric interpretation of motion beyond flat space-time into regions where curvature might exist. If free fall erased gravity, then free fall defined the natural paths of objects in curved space-time. The surfaces on which objects moved were no longer flat planes, but dynamic shapes sculpted by mass and energy. The experience of weight, the feeling of being pressed against the ground, became the result of resisting the natural flow of space-time rather than the result of an invisible pull. This shift in perspective laid the foundation for a new vision of the cosmos. Gravity emerged not as a force, but as the consequence of trying to remain fixed in a curved world. The Earth did not hold us down by pulling. The ground pushed us upward, preventing us from following the space-time path that free fall demanded. The Sun did not tug planets into orbit. It shaped the space-time around them, guiding their motion along curved trajectories that required no force at all. The universe, once imagined as a vast stage of rigid emptiness, had revealed itself as a dynamic landscape whose contours determined the movement of everything within it. Einstein understood that this idea was only the beginning. The equivalence principle provided the conceptual key, but he still required the mathematics capable of expressing how space-time curved and how matter shaped that curvature. The next steps would demand a union of physical insight and geometric language that had never been attempted before. Einstein's happiest thought continued to expand in his mind until it grew into a framework that touched every part of physics. The equivalence principle was no longer a clever observation about falling elevators or drifting spacecraft. It became the seed of a profound truth about the universe, a truth that erased the distinction between gravity and acceleration and placed the behavior of space-time at the center of motion. As he explored the implications of this idea, he found that it changed not only how planets moved, but how clocks ticked, how light traveled, and how the structure of reality itself responded to mass and energy. He considered the behavior of time within the accelerating elevator. If the elevator rose steadily, a beam of light emitted from the floor would travel upward and strike the ceiling. But during that journey, the ceiling would move slightly, causing the light to reach it at a subtly different angle and with a subtly different energy. Einstein realized that this meant time must flow differently at different heights in an accelerating system. A clock near the floor would tick at a slightly different rate than a clock near the ceiling. This was not a trivial effect. It implied that acceleration altered the rhythm of time itself. And because the equivalence principle declared that acceleration and gravity were locally identical, gravity must also affect time. Clocks in a gravitational field must tick at different rates depending on their height. Einstein saw that time dilation, previously associated only with high-speed motion in special relativity, must also arise naturally in the presence of mass. This prediction carried consequences that reached across physics. If gravity influenced time, then the paths traced by objects in a gravitational field were not curved simply because of spatial distortion. They were guided by a deeper structure in which both time and space contributed to the geometry of motion. Einstein began to picture spacetime as a surface whose shape dictated how objects moved. A planet orbiting the Sun followed a path that was straight within this curved geometry, even though it appeared curved when plotted on a flat map. Light traveling past a massive body would follow the geometry as well, bending slightly because the shape of spacetime near mass required it. Time itself would shift depending on altitude, flowing more slowly closer to massive objects. As Einstein followed these thoughts, he realized that the equivalence principle did more than suggest a connection between gravity and geometry. It demanded one. If the experience of free fall eliminated gravity entirely, then gravity could not be an actual force. It had to be the result of being in a state that refused to follow the path that space-time naturally provided. The only observers who felt gravity were those who resisted free fall. A person floating inside a freely falling elevator felt no gravitational pull. A person standing on solid ground, prevented from falling by the surface beneath them, felt the weight of that resistance. Gravity became the sensation of defying geometry. These insights aligned with the growing body of experimental data. The equality of inertial and gravitational mass, revealed through the delicate torsion balance experiments of Eötvös, matched perfectly with the idea that all objects follow the same natural paths in space-time. Their composition did not matter. Their size did not matter. Their internal structure did not matter. Only their location within the curved geometry mattered. Heavy and light objects fell with the same acceleration, not because gravity treated them identically, but because geometry offered them the same path. Einstein applied the equivalence principle to more situations, each revealing another layer of the emerging geometric picture. He saw that even light, which carried no mass, must respond to gravity because it followed the shortest possible path through space-time. If the geometry bent, the path of light bent with it. A beam of starlight skimming past the sun could not continue in a perfectly straight line. It would curve slightly, not because the sun pulled on it, but because the geometry around the sun curved the natural route that photons must take. This prediction became one of the earliest tests of the theory he had not yet fully written. Every insight strengthened Einstein's certainty that he was approaching the correct understanding. The equivalence principle did not offer a complete theory, but it mapped the conceptual territory in which such a theory must be built. It showed that gravity demanded a description based on geometry. It revealed that time and space were inseparable in determining the flow of motion. It united the behavior of clocks, light, and falling objects under a single idea. Most important, it pointed toward a set of equations that would need to express how matter shaped space-time and how space-time guided matter. But the mathematics required to express these ideas was formidable. Einstein knew that the familiar tools of classical physics could not describe curved geometry. He would need a new language, one capable of expressing the curvature of a four-dimensional spacetime. He would need to understand how mass and energy acted as a source for that curvature, and how curvature determined the paths of objects. The next phase of his work would carry him into the realm of Riemann, Ricci, and Levi-Civita, whose mathematical structures waited quietly for the moment when physics would need them. The equivalence principle had revealed the key. Now Einstein needed the machinery to unlock the full structure of the universe. Einstein's journey from the equivalence principle toward a full theory of gravity was marked by a growing awareness that the universe required a mathematical expression far richer than anything classical physics had provided. The insight that free fall erased gravity, that clocks ticked differently at different heights, and that light followed curved paths near mass all pointed toward a single conclusion. Gravity was not a force, it was geometry. But to transform this idea from a conceptual revelation into a physical law, he needed a framework capable of describing how geometry changed from place to place and how matter determined that change. The language he required existed, but it had been created for abstract mathematics, not for the workings of the cosmos. Einstein turned to the work of Bernhard Riemann, who had explored the geometry of curved surfaces long before physicists imagined that space itself could curve. Riemann had developed a way to describe distances and angles on surfaces that bowed, twisted, or stretched in ways that defied flat intuition. These ideas had been considered elegant but largely detached from physical application. To Einstein, they became essential. The universe he sought to describe needed a geometry whose curvature could vary smoothly in response to matter, and Riemann had built the tools that allowed such curvature to be expressed. The notion of a metric, a mathematical object that specified distances in curved spaces, became the foundation of Einstein's thinking. The metric determined how time flowed and how space stretched. It defined the geodesics that free-falling objects followed. It contained the structure from which gravity could emerge. Yet understanding curvature was only part of the challenge. Einstein needed a way to describe how curvature changed from point to point. He found this in the work of Gregorio Ricci and Tullio Levi-Civita, who had developed a systematic method for analyzing curvature in spaces of arbitrary dimension. Their work introduced the concept of a tensor, a mathematical object capable of capturing the full complexity of geometry in a form that did not depend on any particular coordinate system. This independence from coordinates aligned perfectly with Einstein's conviction that the laws of nature must be the same for all observers, regardless of how they described their motion. Tensors offered a way to express physical laws in a language as universal as the geometry they represented. Einstein immersed himself in these ideas, often working through nights, filling notebooks with calculations, and exploring every path that might lead to the correct expression of gravity. The mathematics was difficult even for him. For a time, he partnered with his friend Marcel Grossmann, who helped guide him through the intricate landscape of differential geometry. They explored candidate equations one after another, searching for a structure that matched Einstein's physical intuition. Some early attempts produced promising results, but failed key tests. They might describe curved geometry, but not reduce cleanly to Newtonian gravity in the limit of weak fields. Others captured certain behaviors, but violated the principle that physical laws must remain consistent under transformations between observers. Slowly, Einstein realized that the equations he needed must satisfy several strict conditions. They must reflect the equivalence principle, ensuring that freely falling observers experienced no gravitational force. They must incorporate the geometric structure that special relativity demanded. They must allow curvature to respond to the presence of mass and energy. And they must describe the shape of spacetime in a way that determined the natural paths of both matter and light. These requirements narrowed the possibilities until only one structure remained capable of satisfying them all. The equivalence principle guided every step. It told Einstein that gravity could not be added to the equations of motion as a force term. Instead, it had to emerge naturally from the geometry encoded in the metric. Free fall would be motion along the geodesics determined by that metric. The role of mathematics was not to push objects around, but to describe the shape of spacetime through which they moved. The equations he sought would link curvature to the distribution of mass and energy, allowing the universe to reveal its structure through a continuous dance between geometry and matter. Einstein sensed the destination long before he reached it. Riemann's curvature tensor would measure the bending of spacetime. Ricci's contraction of that tensor would relate directly to the presence of matter. The metric would determine the flow of time and the stretching of space. Light would follow paths dictated by the geometry rather than by any force. Everything pointed toward a coherent description in which gravity became a manifestation of curvature. By the time he assembled these pieces, the universe had revealed its deeper pattern. Gravity was not a mysterious attraction reaching across emptiness. It was the natural motion of objects tracing the geodesics of a space-time shaped by mass and energy. The equivalence principle had been the spark. The mathematics of curvature became the structure. Soon, Einstein would merge these elements into the field equations that reshaped physics forever. Einstein entered the second decade of the 20th century with a vision that had sharpened through years of reflection. He no longer saw gravity as a pull between masses, but as a feature of space-time itself, a feature that required a precise mathematical language to describe. The equivalence principle had revealed the direction forward, and the tools of Riemann, Ricci, and Levi-Civita had provided the vocabulary. What remained was the task of weaving these elements into a single coherent statement of how the universe worked. This task consumed him. It demanded not only physical insight, but an extraordinary mastery of geometry, perseverance through countless false starts, and a willingness to question his own assumptions again and again. In the year 1911, he published early steps toward a relativistic theory of gravity, ideas that showed glimpses of the larger structure he sought. He predicted that gravity would slow the flow of time, and he proposed a preliminary method for describing how light would bend near massive objects. These predictions were grounded in the equivalence principle, but the mathematical framework behind them was still incomplete. Einstein knew that these early attempts did not yet unify geometry and gravity in a self-consistent way. They were fragments of a deeper theory waiting to be assembled. Einstein moved to Zurich and began working closely with Marcel Grossmann, a mathematician and lifelong friend who guided him through the complexities of differential geometry. Grossmann introduced him to the metric tensor, a structure that defined the measurement of time and distance in curved spacetime. The metric was more than a tool. It was the heart of the geometry Einstein needed. If the metric could be determined by physical laws, then everything else would follow. It would define geodesics, the natural trajectories of freely falling objects. It would shape the bending of light. It would describe the stretching of space and the flow of time near massive bodies. The entire behavior of gravity would emerge from the properties of this single structure. But to know the metric, Einstein needed equations that related it to the distribution of mass and energy. The challenge was immense. The equations had to satisfy the principle of general covariance, meaning they must retain the same form under any transformation of coordinates. This requirement was not a matter of mathematical elegance. It reflected Einstein's belief that the laws of nature must not depend on how observers label events. If two observers used different coordinate grids to describe the same region of spacetime, the physical laws had to remain unchanged. Only tensor equations satisfied this requirement. Einstein and Grossmann explored various combinations of geometric tensors that might serve as gravitational field equations. They considered equations built from the Ricci tensor and the metric, comparing their predictions to known physical results. They required that the equations reduce to Newtonian gravity in the weak field and low speed limit, because any new theory had to preserve the success of the old one in familiar circumstances. They also needed the equations to produce energy conservation, a condition that imposed additional mathematical constraints. For a time, Einstein believed he had found the correct form, but doubts soon emerged. Some early versions of the equations lacked the full general covariance he sought. Others failed to reproduce Newtonian gravity accurately. Still others produced nonsensical results for simple scenarios. Einstein faced repeated setbacks, yet each failure tightened the net around the correct structure. With every attempt, the logic of the universe pressed him toward a unique answer. He sensed that he was close. The geometry of space-time, the curvature described by the Riemann tensor, and the distribution of energy in matter all needed to combine in a way that expressed a simple truth. Mass and energy shape the geometry of space-time. The geometry of space-time determines the motion of matter. By the year 1915, Einstein reached a decisive turning point. After years of searching, he realized that the Ricci tensor alone could not express everything necessary to describe curvature. The full structure required the Einstein tensor, a specific combination of geometric quantities that represented space-time curvature in a way that automatically satisfied energy conservation. It contained the Ricci tensor, the scalar curvature, and the metric, bound together in a form that remained covariant under any coordinate transformation. This structure matched his physical intuition. It captured the influence of mass and energy on curvature. It offered a path toward deriving natural motion, and crucially, it reduced to Newtonian gravity when applied to weak fields. Einstein paired this geometric structure with another essential element, the stress-energy tensor, a physical object that contained the density of mass, momentum, pressure, and energy in all its forms, served as the source of curvature. This tensor expressed the content of matter. The Einstein tensor expressed the shape of space-time. The field equations he sought would connect the two. After years of struggle, he wrote the relation in its final form in November 1915. Geometry on one side, matter on the other. A direct connection between the structure of the universe and the energy within it. The meaning of the field equations was profound. Matter told space-time how to curve. Space-time told matter how to move. No force was required. No instantaneous action at a distance remained. Gravity became the elegant interplay between mass and geometry, a natural expression of the shape of the cosmos. Einstein soon discovered that these equations possessed solutions far beyond his initial expectations. One of the earliest came from Carl Schwarzschild, who solved the equations exactly for the gravitational field around a spherical mass. This solution revealed the precise curvature of space-time around stars and planets, and laid the groundwork for understanding black holes many decades later. Its appearance so soon after the formulation of the equations confirmed that the field equations were not only mathematically correct, but physically powerful. The stage was now set for the universe to respond. The equations were ready. The predictions were clear. The next test would come not from theory, but from the sky itself. Einstein spent the closing months of 1915 in a state of intense concentration, refining the equations that now carried the weight of the universe within them. The field equations were not merely an elegant mathematical structure. They were a set of physical statements about how every event unfolded in the cosmos. They described how the presence of matter altered the rhythm of time, how distances stretched or compressed, and how the flow of motion followed the geodesics carved into space-time. Once written, these equations became the foundation upon which the rest of modern gravity would stand. Yet Einstein knew that beauty alone could not validate them. They needed to speak with the voice of nature. His first tests involved the familiar world of slow-moving planets and weak gravitational fields. Any theory that hoped to replace Newtonian gravity had to recover classical predictions in situations where Newton's laws had been confirmed for centuries. Einstein examined the limit in which velocities were small and space-time curvature modest. In that limit, the field equations reduced to a form strikingly similar to Newton's inverse square law, but with a refinement that matched the precision of astronomical observations. The equations did not merely recover the classical result, they sharpened it. When Einstein applied his equations to Mercury's orbit, the stubborn anomaly that had challenged astronomers for generations emerged naturally. The equations predicted the additional drift in the perihelion with exact precision. The unexplained residue that had refused all classical explanations was not an error. It was a fingerprint of space-time curvature near the Sun, and the field equations captured it flawlessly. This success affirmed that the theory was not only mathematically coherent, but physically necessary. The long-standing mystery of Mercury's motion had been solved without invoking unseen planets or ad hoc adjustments. Einstein had revealed that the inner regions of the solar system were regions of measurable curvature. The orbits were not carved into flat space, but traced through a gently warped geometry that only a relativistic theory of gravity could describe. The anomaly was no longer a discrepancy, it was evidence. Encouraged by this triumph, Einstein turned to the second major prediction of his theory. Light, he realized, must also respond to curvature. A beam passing near the Sun should bend slightly as it followed the natural path determined by the metric. His earlier work in 1911 had predicted a bending effect, but the full field equations revealed a value twice as large as his preliminary estimate. This refined prediction became one of the most dramatic tests of the emerging theory. If starlight passing near the Sun during a total eclipse shifted by the amount the field equations required, then gravity was indisputably geometric. If it did not, the theory would fall. At the same time, another consequence of the equations emerged. Time itself flowed differently in regions of different gravitational strength. A clock held at the surface of Earth ticked more slowly than a clock lifted far above it. This gravitational redshift had been conceptually sketched from the equivalence principle, but now the field equations provided its exact form. It became clear that gravity influenced every process in which time played a role, including the frequency of light emitted from atoms. If the theory was correct, light climbing out of a gravitational field would lose energy, shifting slightly toward the red. The effect was extraordinarily small near Earth, but it was real, and it offered another path toward experimental confirmation. Einstein pushed deeper into the implications of the equations. He realized that they describe not only the geometry around stars and planets, but the behavior of space-time everywhere. Pressure and energy contributed to curvature alongside mass. Moving matter produced distortions that depended on momentum. Even empty space was no longer truly empty, for the geometry itself had structure that could evolve according to the distribution of energy. The equations were universal. They applied to phenomena within the solar system, to the motion of binary stars, to the bending of light across immense cosmic distances, and to the expansion of the universe itself. During this period, Karl Schwarzschild, serving at the front lines during the Great War, sent Einstein an exact solution to the field equations for the spacetime surrounding a spherical mass. Einstein received the letter with astonishment. He had believed that finding such a solution might require months of work, yet Schwarzschild had obtained it almost immediately after the equations appeared. The solution revealed the precise form of spacetime curvature around stars and planets. It reproduced Newtonian gravity for weak fields, yet carried within it the seeds of far more dramatic structures that scientists would uncover decades later. At the time, Einstein focused on its immediate implication. The existence of an exact solution confirmed the power and internal consistency of the field equations. They were not only physically correct, they were mathematically fertile. As Einstein and others continued to explore the theory, its conceptual clarity grew. Motion no longer required invisible forces. A planet followed a geodesic in curved spacetime. Light traced the same type of path, bending, not because it possessed mass, but because it moved through the same geometric structure that guided all trajectories. Time shifted in the presence of mass because the metric itself changed, altering the length of intervals. Space warped. Distances transformed. Every effect previously attributed to gravity became a consequence of the structure of spacetime. Einstein had built the foundation of a new universe, one in which geometry controlled motion. But a theory gains strength only when the universe itself responds. The next chapter in this unfolding story would come from the sky, as astronomers prepared to test whether starlight truly curved as the field equations demanded. Einstein entered the final weeks of 1915 with the sense that the universe had finally revealed its deeper order. The field equations now stood complete, linking curvature to the distribution of mass and energy with a precision unlike anything physics had ever possessed. Yet the meaning of these equations continued to unfold. They were not simply a replacement for Newtonian gravity. They were a new way of understanding motion, time, and structure at every scale. Even before the first astronomical tests arrived, Einstein sensed that the equations carried more consequences than he could yet imagine. Their logic extended far beyond the solar system. They reached into realms untouched by observation, realms where space-time itself might behave in unfamiliar ways. As he examined the equations more closely, he discovered that they allowed for ripples in the geometry of space-time, disturbances that could move outward like waves. These gravitational waves were not forces pushing through a medium, nor were they mechanical vibrations in a substance. They were changes in curvature that propagated at the speed of light, consistent with the rules of special relativity. Einstein initially hesitated in describing them, unsure of how to interpret certain solutions, but the mathematics was clear. If mass moved in just the right way, space-time would respond by sending out waves that carried energy across the cosmos. The idea that space-time could pulse and vibrate was astonishing, yet it arose naturally from the equations he had just written. Gravity had become dynamic. At the same time, he reflected on the meaning of motion in this new geometric world. A free-falling object did not require an external cause to accelerate. It simply followed the geodesic shaped by the metric. The only observers who felt gravity were those who resisted free fall, those who forced themselves away from the natural curve of space-time. Standing on Earth was not a state of calm rest. It was a continuous upward push against the geodesic that space-time offered. The familiar sensation of weight was nothing more than the body experiencing the resistance that prevented it from falling along its natural path. For Einstein, this redefinition of gravity as the absence of force rather than its presence became one of the most profound shifts in physical understanding. He also recognized that the equations held the potential to reshape the study of the universe at large. The field equations did not specify whether spacetime must remain static. They allowed for expansion, contraction, or more complex evolution, depending on how matter and energy were arranged. This flexibility hinted that the cosmos need not be fixed. It could change over time, a possibility that classical physics had never entertained. Although Einstein himself initially sought a static universe and later introduced a term to enforce this, the equations did not require stillness. They carried within them the capacity for a dynamic cosmos. Meanwhile, the Schwarzschild solution continued to reveal surprising structure. Though Einstein did not explore its most extreme implications at the time, the geometry described by Schwarzschild contained a boundary beyond which not even light could escape. This region, which later generations would call a black hole, remained only a mathematical curiosity for decades. But even in its nascent form, the solution showed that the equations possessed a depth that extended beyond immediate experience. The geometry near a massive object could grow so intense that it reshaped space and time in dramatic ways. Einstein also explored how his equations might describe light traveling through curved spacetime. A beam passing near a massive object would bend twice as much as Newton's corpuscular theory predicted. This difference became a critical test. If future observations confirmed the relativistic prediction, the theory would gain extraordinary strength. If not, its foundation would crumble. Yet Einstein trusted the logic of the equations. They flowed naturally from the equivalence principle, from the geometry of Riemann, and from the empirical constraints of special relativity. Their internal consistency convinced him that the predicted bending must be correct. The theory continued to deepen. Einstein's equations implied that time would slow near massive objects, an effect that extended far beyond the Earth. In strong gravitational fields, this slowing could become dramatic. Light escaping from such regions would shift toward the red, not because of any external influence, but because the flow of time itself differed. This gravitational redshift became another prediction awaiting verification. Though the first direct terrestrial test would come decades later, Einstein already understood that such an effect was an inevitable consequence of the geometry he had uncovered. Each new realization reinforced a central theme. The universe behaved according to geometry. The curvature of spacetime dictated the trajectories of planets, the bending of light, the ticking of clocks, and the motion of all matter and energy. No invisible force acted across distance. Instead, the geometry evolved according to the distribution of mass, and all objects responded by following the paths that this geometry defined. Gravity had become an expression of the shape of the cosmos. By the end of 1915, Einstein had completed one of the greatest intellectual transformations in history. He had replaced a centuries-old conception of force with a geometric understanding of motion. Yet the ultimate test of his achievement would come from astronomy. The equations now stood ready. The predictions were clear. The universe itself would decide whether the structure he had uncovered reflected physical truth. In the early years after Einstein completed his field equations, the world had not yet grasped the scale of the transformation he had created. Only a handful of physicists understood the depth of the shift from force to geometry, and even fewer realized how many predictions the new theory carried within its structure. The equations were not abstract symbols. They were precise instructions describing how nature behaved. If they were correct, the universe would reveal their truth in ways that no earlier theory could match. The first signs of this truth appeared in the realm that had inspired Einstein from the beginning, the realm of planetary motion. Mercury, whose orbit had resisted explanation for decades, became the first celestial witness to the new geometry. Einstein revisited the problem with the full machinery of the field equations. He treated the sun not as an object exerting a force, but as a source of curvature that shaped the space-time surrounding it. Mercury, moving close to this intense curvature, traced a path that differed subtly from the one predicted by Newtonian gravity. When Einstein performed the calculation, he found the exact value of the long, puzzling drift in Mercury's perihelion. The number that emerged from his equations matched observational records with stunning precision. This agreement was not a coincidence. It revealed that the orbit of Mercury was a natural geodesic in the curved space-time near the Sun. What astronomers had interpreted as a deviation was simply the Earth-bound perspective of a trajectory unfolding within a curved universe. This triumph sent a quiet signal into the scientific world. Gravity had spoken through Mercury, and its voice matched Einstein's prediction. Yet even this success could not carry the full weight of the new theory. For many scientists, the decisive test would come from light itself. If space-time curved around mass, then light traveling near the Sun should bend by a small but measurable amount. The idea that gravity could alter the path of something with no mass seemed radical, yet Einstein's geometry demanded it. The bending would be subtle, visible only when stars appeared close to the edge of the Sun during a total eclipse. Most of the time, those stars were hidden by the solar brightness. Only the shadow cast by the moon could reveal them. Einstein knew this prediction would either lift the theory into the realm of confirmed truth or cast doubt upon it. The science required no interpretation. Either starlight near the Sun would shift by the predicted amount, or it would not. The opportunity arrived in the year 1919, when total solar eclipses crossed regions accessible to expeditions equipped with photographic plates and precise instruments. British astronomers, including teams led by Arthur Eddington on the island of Príncipe and Andrew Crommelin in Brazil, set out to measure the expected deflection. Their instruments captured starfields during the eclipse and compared them to reference images taken when the sun was elsewhere in the sky. The deflections were small, but the photographic plates recorded subtle shifts in the apparent positions of several stars. When the measurements were analyzed, they aligned with Einstein's predicted value. It was not a perfect experiment. The conditions were difficult, the weather inconsistent, and the uncertainties real. Yet the results, confirmed later with improved methods, pointed toward the bending of light by the curvature of spacetime. For the first time, the geometry of the universe revealed itself directly to human eyes. Starlight bent around the sun not because the sun pulled on it, but because spacetime itself curved, guiding the path that photons followed. This demonstration carried profound meaning. It showed that the world described by Einstein's equations was not merely mathematically consistent. It was physically real. Newspapers around the world published the results, and Einstein, previously known mainly to specialists, became a figure recognized far beyond the realm of physics. But beneath the excitement lay a deeper shift. The victory of the eclipse experiments showed that gravity was not a force, but a manifestation of geometry. At the same time, another prediction of the theory approached experimental confirmation. Einstein had shown that time flowed differently in gravitational fields. A clock placed at a lower altitude, closer to Earth's mass, would tick more slowly than a clock raised to higher elevation. This gravitational redshift was extraordinarily small near Earth, but still detectable with careful design. Early attempts to measure it used astronomical observations, though these efforts faced challenges due to the complexity of stellar atmospheres. The definitive measurement would come decades later through the Pound-Rebka experiment, which used gamma rays traveling a short vertical distance inside a tower. The shift in frequency matched the prediction precisely, confirming that time itself responded to curvature. Although this experiment lay in the future, its conceptual foundation rested firmly upon the work done during Einstein's era. These confirmations were more than isolated successes. They demonstrated that the field equations, though complex, captured the structure of physical reality. They revealed that geometry governed not only the motion of planets, but the propagation of light and the flow of time. The curved world Einstein had imagined was no longer theoretical. It had been measured. It had appeared on photographic plates. It had revealed itself in the frequencies of photons and the ticking of clocks. The scientific community gradually shifted from skepticism to recognition. General relativity, once considered a daring extension of special relativity, became one of the most thoroughly tested theories in physics. Its predictions are held in the solar system, in the laboratory, and in astronomical observations. Each new test strengthened the conclusion that gravity was not an interaction transmitted across space, but the shape of spacetime itself. But even these early triumphs represented only a fraction of what the theory implied. If spacetime could bend, it could also ripple. If it could shape planetary orbits, it could also sculpt the structure of galaxies. If it could stretch time, it could influence the evolution of the entire cosmos. The next great chapter in Einstein's story lay not in the steady pull of familiar gravity, but in the possibility that spacetime could vibrate, carrying information across the universe in the form of gravitational waves. Einstein's theory had begun to reveal itself through the motion of planets, the bending of starlight, and the shifting of time. Yet these early confirmations were only the first signs of a universe reshaped by geometry. As physicists and astronomers examined the implications of the field equations more deeply, they saw that the theory carried predictions that reached far beyond the solar system. The bending of light was dramatic, but it was only one consequence of curved spacetime. Other effects lingered quietly beneath the surface, waiting for instruments of greater sensitivity and for the patience required to observe them. Among these effects was the slow warping of time in strong gravitational fields and the subtle influence of curvature on the paths of signals and particles. These manifestations would be explored over decades, gradually revealing the precision and power of Einstein's vision. One of the earliest avenues of investigation involved the flow of time in gravitational fields. Although Einstein had offered clear predictions, the effect near Earth was extremely small. A clock held at the top of a tower would run slightly faster than a clock at the bottom, not because of mechanical imperfections, but because the geometry of spacetime differed at the two heights. The field equations described this effect with clarity, yet verifying it required experimental tools that did not yet exist. Physicists attempted to detect gravitational redshift by observing light emitted from massive stars, but atmospheric turbulence and stellar processes complicated their measurements. Despite these difficulties, the underlying principle remained firm. As the theory matured, so did the techniques needed to test it. Einstein continued to refine the applications of his equations, examining how curvature influenced not only light and time, but also the structure of orbits. The precise value of Mercury's perihelion shift became a touchstone for the theory, demonstrating that the field equations extended Newtonian predictions in the exact way needed to match reality. As new measurements of planetary positions emerged, they continued to align with the relativistic corrections. The orbits of Venus and Earth showed tiny refinements under the lens of the new geometry. These refinements were too subtle for 19th century observers to detect, but the 20th century would bring ever more precise ephemerides that confirmed the predictions again and again. The bending of light also invited further examination. Although the 1919 eclipse expeditions had captured the essential effect, later observations took advantage of improved photographic plates, stabilized telescopes, and more refined analytical techniques. Radio astronomy eventually provided measurements of starlight and quasar signals passing near the Sun with much greater precision than optical plates allowed. These results confirmed the relativistic prediction to impressive accuracy. Every test strengthened the emerging picture. Matter and light moved not through a static background, but through a curved spacetime whose shape revealed the presence of mass. As Einstein explored additional consequences of the theory, he recognized that the curvature of spacetime would influence not only photons, but also the passage of signals between distant objects. The paths of radar pulses sent toward planets and reflected back to Earth would reveal slight time delays due to the warping of spacetime. Although this effect would not be detected until the mid-20th century, its conceptual foundation rested squarely within the framework Einstein had built. The geometry of spacetime shaped every route through which information traveled. Yet the most compelling early manifestation of the theory, apart from Mercury's orbit and the bending of light, lay in the prediction that time slowed in strong gravitational fields. Although no tower-based experiment in Einstein's lifetime could detect this shift, the effect held profound implications. It implied that clocks on satellites would tick differently from clocks on Earth, that the rhythm of time near massive stars would differ from that far away, and that the frequencies of atomic transitions would shift predictably with changes in gravitational potential. These insights, grounded in the field equations, opened pathways that later generations would verify through exquisitely sensitive measurements. But even in Einstein's era, the conceptual picture was complete. Time itself was part of the geometry, and geometry responded to mass. As more scientists embraced the new theory, they recognized that general relativity was not merely a correction to Newtonian gravity, but a structural transformation. It described gravity in a way that provided consistent predictions for phenomena across scales. It explained why the speed of light remained constant. It showed why gravitational influence could not propagate instantaneously. It unified the motion of planets, the bending of light, and the flow of time into a single geometric framework. The successes of the theory were not isolated victories. They were signs that the universe truly behaved according to the curvature of spacetime. Even so, the theory faced challenges in its early years. Many physicists were cautious, unsure whether geometric reasoning could withstand the full scrutiny of observation. They questioned whether the bending of light had been measured with sufficient accuracy. They wondered whether the Mercury anomaly could have other explanations. But as evidence accumulated, skepticism gave way to acceptance. General relativity gradually earned its place as a central pillar of modern physics. It did so not through philosophical argument, but through experimental confirmation, the only measure Einstein truly valued. By the mid-20th century, the experiments Einstein had envisioned began to materialize. The Pound-Rebka measurement of gravitational redshift confirmed that time flowed differently in stronger gravitational fields. Radar ranging demonstrated the additional delays predicted by curved spacetime near the Sun. Observations of binary systems revealed the influence of relativity in orbital motion. Each new test strengthened the conclusion that spacetime was not an empty stage, but a dynamic entity shaping every motion within it. These early confirmations formed the foundation of a deeper realization. If spacetime could bend, it could also ripple. If geometry governed planetary motion and the flow of time, it might also transmit energy through waves that traveled across the universe. The next frontier lay in the dynamic nature of spacetime itself, a frontier that would take decades to measure, but whose existence Einstein had already foreseen in the equations he completed in 1915. Einstein's theory had now demonstrated its strength through the most delicate mechanisms of nature. It had accounted for Mercury's anomaly, revealed the bending of starlight, and described how time itself shifted under the influence of mass. These accomplishments were remarkable, yet Einstein sensed that the equations contained more. They allowed for behaviors that no previous theory of gravity had ever considered. They hinted that spacetime was not merely curved in response to matter, but capable of evolving and carrying information. Even before experiments could probe these predictions, the mathematics made their presence undeniable. The final confirmations awaited decades of technological progress, but their conceptual seeds were planted within the earliest years of general relativity. One of the first signs of deeper structure lay in the behavior of time near dense objects. The theory predicted that clocks would slow dramatically as one approached the surface of a massive star. This effect, small near Earth, became immense near stellar remnants, whose densities far exceeded anything found in the solar system. Although such objects were not yet observed in Einstein's lifetime, astronomers would soon uncover white dwarfs, whose gravitational pull created measurable shifts in the spectra of light emitted from their surfaces. These gravitational redshifts matched the predictions of general relativity and marked one of the earliest astrophysical confirmations of the theory beyond the solar system. The geometry near dense stars was no longer an abstract idea. It had become an observable reality. At the same time, physicists began to explore how relativity influenced the motion of binary star systems. Although precise measurements would not arrive until later in the century, the conceptual framework was already clear. In systems where two massive stars orbited one another at close distance, the curvature of spacetime would alter their trajectories in measurable ways. Their orbital periods would reveal tiny deviations from Newtonian predictions, deviations arising from the relativistic corrections encoded in Einstein's equations. These insights prepared the ground for discoveries that would emerge decades later through radio observations of pulsars, but the logic connecting these ideas to the field equations was already firmly established. Other predictions awaited even greater technological advances. Einstein had shown that signals traveling near massive bodies would experience delays due to the curvature of spacetime. Radar pulses sent to planets such as Venus would take slightly longer to return when their paths passed close to the Sun. Although the equipment to test this prediction did not exist during Einstein's era, later generations would measure these delays with extraordinary accuracy, confirming yet another aspect of the theory. Each effect extended the reach of relativity beyond the familiar world into new realms of measurement and observation. While these experimental possibilities grew, theoretical investigations continued to reveal the richness hidden within the field equations. The Schwarzschild solution, discovered so soon after the equations were written, demonstrated that spacetime near a spherical mass possessed regions of intense curvature where time slowed dramatically and where light could be trapped. Although the extreme implications of this solution were not fully explored until decades later, the geometry it described hinted that the universe contained phenomena far more complex than classical physics had ever considered. The existence of black holes, though not yet identified, was already encoded in mathematics. As the scientific community gained confidence in Einstein's theory, the eclipse measurements and the explanation of Mercury's orbit took on new significance. They were not isolated verifications. They were the first points of contact between theory and observation in a larger tapestry that would eventually include gravitational time dilation, radar delays, orbital decay in binary systems, and the propagation of gravitational waves. Each confirmation strengthened the idea that space-time was the central actor in gravity. No force transmitted across emptiness. No instantaneous influence connected distant masses. Instead, the geometry of the universe evolved according to the distribution of energy, guiding every motion in a way consistent with both relativity and observation. In this early period of general relativity, the world began to recognize that Einstein had uncovered a structure capable of describing not only the familiar gravitational phenomena of the solar system, but the dynamic behavior of the universe itself. The field equations contained the possibility of an expanding cosmos, the behavior of massive stars, the bending of distant light, and the propagation of waves in the fabric of space-time. Many of these implications would take decades to be explored experimentally, yet the logic was already complete. The early confirmations of the theory created a quiet but decisive shift. The new understanding of gravity no longer stood as a speculative extension of special relativity. It had become an empirically grounded framework that could explain what Newtonian gravity could not. The bending of light, the shifting of time, and the correction to planetary orbits revealed that geometry governed motion. The theory had passed every test placed before it, and its predictions continued to unfold with remarkable coherence. Yet one of the most extraordinary implications of Einstein's equations had not yet been observed. If space-time could bend, then it could also ripple. The universe might carry vibrations generated by massive objects in motion, and these vibrations might travel across cosmic distances, revealing the dynamic nature of geometry itself. This idea, once a mathematical curiosity, would eventually become one of the most significant confirmations of general relativity. But before the world could detect those waves, it needed to understand their meaning. Einstein had shown that space-time could curve, that it could guide the motion of planets and the bending of light, that it could slow the ticking of clocks and shape the flow of time itself. But hidden within the field equations was an even more astonishing realization, one that reached far beyond the familiar image of gravity as a gentle, steady influence. The equations did not merely describe a static curvature surrounding massive objects. They allowed that curvature to change, to shift, and to propagate. They revealed that space-time could behave like a physical entity, capable of transmitting information in the form of waves that traveled at the speed of light. These waves were not disturbances in a material medium. They were changes in geometry itself. Einstein recognized their existence soon after completing the field equations, though the implications were so extraordinary that even he hesitated to accept them fully. He began by considering what would happen if massive bodies moved rapidly, especially if they accelerated. In Newtonian gravity, such motion would produce immediate changes throughout space because the force acted instantaneously. But general relativity allowed no such instant influence. Any change in the distribution of mass or energy had to propagate outward at a finite speed. When Einstein examined the weak field approximation of his equations, he found that space-time curvature could oscillate in a way analogous to waves on a surface. These oscillations carried energy and could travel across the universe without losing their identity. They were not mere mathematical artifacts. They were physical predictions, rooted in the same geometric framework that had already explained Mercury's orbit and the bending of starlight. Einstein published the first analysis of gravitational waves in 1916. His work showed that disturbances in spacetime would propagate in a pattern similar to waves, stretching and squeezing distances in perpendicular directions as they passed. The effect was extraordinarily small for any realistic source, which made detection seem far beyond the reach of contemporary instruments. But the theory was clear. If matter moved in certain ways, especially in asymmetric motion such as orbiting bodies, spacetime would radiate energy through gravitational waves. These waves would carry information about the motion of their sources, revealing events far more dramatic than anything visible through ordinary light. Yet the interpretation of gravitational waves initially sparked confusion, even for Einstein. General relativity was a highly non-linear theory, and separating physical effects from coordinate artifacts required great care. For a time, Einstein doubted whether the waves he had found were real or merely products of particular coordinate choices. Later calculations resolved the uncertainty. Gravitational waves were indeed physical. They carried measurable energy, and their existence followed directly from the structure of the field equations. Although Einstein eventually returned to the conclusion that the waves were real, the complexity of mathematics delayed broader acceptance. It would take decades for the first indirect evidence to emerge. Meanwhile, the scientific community explored the implications of gravitational radiation with increasing interest. If two massive objects orbited each other, their motion would cause them to lose energy gradually as gravitational waves radiated outward. This loss of energy would cause their orbit to shrink slightly over time. For ordinary stars, the effect was too small to measure. But in systems containing extremely dense objects such as neutron stars, the influence could become significant. The opportunity arrived in the 1970s with the discovery of a binary pulsar system by Russell Hulse and Joseph Taylor. The system consisted of two neutron stars orbiting one another with remarkable speed. Pulsars emit beams of radio waves with such regularity that they function as cosmic clocks. By tracking these beams over years, Hulse and Taylor measured the orbital decay of the system with extraordinary precision. The orbit shrank at exactly the rate predicted by general relativity, due to the emission of gravitational waves. No other explanation matched the observations. The result provided the first strong evidence that gravitational waves carried real energy and that spacetime behaved dynamically in the way Einstein had predicted. The discovery earned the Nobel Prize and marked a turning point in the understanding of gravity's most elusive phenomenon. But indirect evidence, no matter how precise, could not reveal the full nature of gravitational waves. The ultimate confirmation would require detecting the waves directly, capturing the faint oscillations in spacetime as they pass through Earth. This task demanded engineering of unprecedented sensitivity, capable of measuring changes smaller than the width of a proton across kilometer-scale distances. Physicists began to design this new generation of detectors in the late 20th century, guided by the principles of laser interferometry. Among these projects, the Laser Interferometer Gravitational Wave Observatory, known as LIGO, became the most ambitious. LIGO-S detectors used long perpendicular tunnels in which laser beams traveled back and forth, comparing their distances with extraordinary precision. If a gravitational wave passed through Earth, it would stretch one tunnel slightly while compressing the other. The difference, though tiny, would produce a measurable shift in the interference pattern of the returning laser beams. Achieving the sensitivity required for such a measurement demanded breakthroughs in vibration isolation, vacuum engineering, optical stability, and seismic filtering. The scientists and engineers working on LIGO spent decades refining every component, building a system capable of detecting fluctuations in spacetime itself. As the 21st century began, LIGO's upgraded detectors reached the sensitivity needed to observe gravitational waves generated by massive astrophysical events. On a quiet day in September of the year 2015, the signal finally arrived. Two black holes, far beyond our galaxy, spiraled together and merged, releasing a burst of gravitational energy that traveled across the cosmos for more than 1 billion years. When the wave reached Earth, it produced a tiny oscillation in the detectors, an imprint of the changing curvature of space-time. The measurement matched the predictions of general relativity with striking precision. It was the first direct detection of gravitational waves and the first direct observation of black hole mergers. The discovery confirmed Einstein's prediction in the most dramatic way possible. Space-time was not only curved, it was dynamic. It vibrated, carried information, and acted as a medium through which the most violent events in the universe could be felt across unimaginable distances. With this detection, the geometric vision of gravity reached a new stage. The field equations had revealed that the universe was alive with motion, far more subtle and powerful than classical physics had ever imagined. Einstein's prediction of gravitational waves had transformed from a mathematical consequence into a physical reality. With the first direct detection complete, the scientific world entered a new era, one in which space-time itself became an observable participant in cosmic events. Yet the story of gravitational waves did not end with that first historic signal. It broadened, deepened, and expanded into a discipline that allowed humanity to listen to the universe in a new way. LIGO's achievement marked the beginning of gravitational wave astronomy, a field built not on light, but on the dynamic fabric of space-time. To understand how this transformation unfolded, one must follow the evolution of the detectors, the refinement of their methods, and the astonishing range of phenomena they revealed. After the 2015 detection, the LIGO team analyzed the signal meticulously. The waveform matched the expected pattern of two black holes spiraling inward, radiating energy through space-time, and merging into a single, larger black hole. The signal revealed the masses of the two original objects, their distance from Earth, the energy emitted, and the characteristics of the final black hole that formed. No other type of astronomical observation could have provided such detailed information about such an event. Light could not escape the region of the merger. Electromagnetic telescopes could not see it. Yet space-time itself carried the story intact across 1 billion light-years. This success strengthened scientists' commitment to improving the sensitivity of gravitational wave detectors. Advanced LIGO continued to refine its components, using higher power lasers, better mirror suspensions, and more sophisticated noise reduction systems. The Virgo detector in Europe joined the effort, enabling triangulation of wave sources and more accurate localization on the sky. Later, the Kagra detector in Japan added further global reach, bringing underground engineering and cryogenic mirrors into the international network. Together, these observatories formed a system capable of detecting a range of gravitational wave signals with increasing precision. Each new detection revealed another facet of the gravitational universe. More black hole mergers appeared in the data, each with its own mass, distance, and history. Some involved smaller stellar mass black holes. Others revealed unexpectedly large ones, indicating that nature could produce massive stars or combination events far beyond previous assumptions. The waveforms carried the signature of general relativity through every cycle. The inspiral, the merger, and the ring-down phases matched theoretical predictions to remarkable accuracy. These signals allowed researchers to test Einstein's equations in the strongest gravitational fields accessible to observation. No deviations appeared. Even near the most extreme regions of space-time, general relativity remained consistent. The detectors also captured a fundamentally different type of event. In 2017, LIGO and Virgo recorded the gravitational waves emitted from two neutron stars spiraling together. Unlike merging black holes, neutron star collisions produce intense electromagnetic radiation. Their gravitational wave signal was followed by a burst of light detected by telescopes around the world. This event marked the first time astronomers observed the same cosmic occurrence through both gravitational waves and electromagnetic signals. The combined observations revealed the physics of neutron star interiors, the origins of heavy elements such as gold and platinum, and the behavior of matter under incredible densities. It also established gravitational wave astronomy as a partner to traditional observational methods. These detections proved that gravitational waves carried more than confirmation of general relativity. They offered a new way to explore the universe. They revealed regions that light could not probe. They allowed astronomers to study black holes directly and to learn how binary star systems evolve. They provided measurements of cosmic distances independent of traditional methods. They allowed scientists to infer the expansion rate of the universe by comparing gravitational wave signals with accompanying electromagnetic observations. In every case, the predictions of general relativity guided the interpretation of the data. Curved spacetime, dynamic and expressive, had become an instrument for understanding the cosmos. As detectors improved, they began to probe quieter signals. Scientists searched for continuous gravitational waves from rapidly spinning neutron stars, for stochastic backgrounds produced by countless weak sources throughout the universe, and for signals from supernovae and other violent events. Each target required new analytical techniques and deeper understanding of noise patterns, but the motivation remained the same. Space-time carried information, and that information could reveal aspects of the universe that no other method could access. The success of LIGO and its global partners also inspired the development of new types of detectors. Proposals for space-based observatories, such as the Laser Interferometer Space Antenna, emerged with the promise of detecting signals from supermassive black hole mergers and other phenomena too low in frequency for ground-based instruments. Pulsar timing arrays, another technique, used the regular pulses of distant neutron stars as detectors for gravitational waves passing between Earth and those stars. These arrays provided evidence of a background of low-frequency waves, likely produced by binary supermassive black holes scattered across the universe. Although such results represented a different observational regime, they were rooted in the same fundamental prediction of Einstein's equations. Through all these developments, the nature of gravitational waves remained clear. They were not disturbances in matter, not particles traveling through space, not vibrations of any physical medium. They were changes in the geometry of space-time itself. Their detection did more than confirm a prediction. It revealed that the universe possessed a physical structure capable of motion, capable of carrying energy, and capable of recording the most violent cosmic events in its very shape. Gravitational wave astronomy had turned Einstein's insight into a new sensory window on the universe. The curvature of spacetime was no longer a silent background. It had become a dynamic storyteller, carrying the signatures of distant black holes, neutron stars, and cosmic collisions across unimaginable distances. And through these stories, a deeper realization emerged. If spacetime could ripple across the universe, it could also govern the unfolding of the universe itself. Einstein's waves had become real, their signatures measured, their energy traced, their origins reconstructed from the faint trembling they left in detectors on Earth. But gravitational waves were more than a new kind of signal. They were living proof that spacetime was not passive. It responded to motion, carried information, and linked distant events through its own geometry. With each new detection, physicists found themselves listening to the universe in a way no earlier generation had imagined. What began as a mathematical feature of the field equations had grown into a bridge between theory and observation, revealing how gravity behaved in its most extreme settings. As data accumulated, scientists began to use gravitational waves not merely as confirmations of general relativity, but as tools for probing regions of the cosmos that had once been inaccessible. Each waveform carried details about the masses of the objects involved, the energy radiated, and the geometry of the merger. The inspiral of two black holes produced a rising frequency known as a chirp, a sound like a brief cosmic sweep upward in pitch. The details of this chirp encoded the entire history of the orbit. It told how quickly the bodies approached each other, how much energy the system lost, and how space-time responded at every moment. None of this required light. None of it required matter. The information traveled on the curve of spacetime itself. This power became clear in the growing catalogue of detections. Some mergers involved black holes far heavier than those produced by ordinary stellar collapse, suggesting that earlier generations of stars or hierarchical mergers might play a role in their formation. Others revealed near-perfect consistency with the predictions of the field equations. The ring-down phase of a newly formed black hole, for example, matched the characteristic oscillations expected from the curvature described by the Schwarzschild or Kerr solutions. Scientists use these oscillations to test whether black holes conform to the geometric structures predicted by general relativity. Every test so far affirmed the theory. The interplay between gravitational wave observations and electromagnetic astronomy deepened as well. The neutron-star merger of 2017, accompanied by light across the spectrum from gamma rays to radio, provided a direct measurement of how spacetime and matter behave together in the most violent collisions known. The gravitational signal revealed the masses and orbital behavior of the stars. The electromagnetic signal revealed how heavy elements formed as the collision scattered material into space. Something long suspected finally gained direct confirmation. Elements like gold and platinum, formed through rapid neutron capture, originated in cataclysmic mergers of neutron stars. The geometry of spacetime had become a guidebook for understanding chemical origins. As detectors continued to improve, scientists began to explore more subtle signals. They searched for continuous waves from rapidly spinning neutron stars, whose slight imperfections would produce stable, rhythmic distortions in spacetime. They searched for a faint background produced by countless unresolved sources throughout the universe. This background, if detected in detail, could reveal the history of black hole mergers or even leftover signatures from the early universe. Pulsar timing arrays provided hints of such a background, detecting correlated shifts in the timing of pulsar signals across the sky. These shifts matched the expected signature of slow, rolling gravitational waves. Though different in scale from the rapid signals recorded by ground-based detectors, they emerged from the same equations Einstein completed in 1915. Meanwhile, theoretical work explored how gravitational waves interacted with the curvature of spacetime on cosmic scales. They could stretch and compress the distances between galaxies by tiny amounts. They could influence the propagation of other signals. They could traverse regions of the universe opaque to light, revealing structures hidden behind dust, gas, or extreme gravitational fields. This transparency made gravitational waves uniquely powerful as probes of environments inaccessible to traditional astronomy. Each of these developments strengthened the conclusion that general relativity captured gravity in its true form. The success of the theory did not rest on any one observation. It rested on the coherence of all of them. Mercury's orbit, light bending, gravitational redshift, time dilation, radar delay, orbital decay in binary pulsars, and the direct detection of gravitational waves all told the same story. Gravity was geometry. Motion did not require forces. It required geodesics carved into space-time. Light did not curve because of attraction. It curved because space-time itself bent. Clocks did not shift because of any mechanical influence. They shifted because time was part of the geometry. The emergence of gravitational wave astronomy brought the geometric nature of gravity into focus more strongly than ever. It showed the universe not as a static arena, but as a living structure. Every motion, every collision, every orbit, every collapse, every ripple in space-time was a reminder that geometry controlled all motion. These discoveries did more than confirm Einstein's theory. They deepened the human understanding of gravity by showing that even the most violent cosmic events express the same geometric principles that guided Mercury around the Sun. As the field matured, scientists realized that gravitational waves provided a bridge between the worlds of strong and weak gravity, between the structure of galaxies and the dynamics of black holes, between the quiet passage of time and the explosive release of gravitational energy. With this understanding came a deeper appreciation that curvature extended far beyond local phenomena. It governed the shape and destiny of the universe on the largest scales. The universe had long appeared as a vast collection of objects drifting through an empty background, a stage on which matter moved while space itself remained silent. General relativity overturned that picture entirely. Einstein's field equations revealed that space and time were not inert. They could stretch, bend, twist, and evolve. They could shape the motion of galaxies, guide the paths of photons, and even govern the expansion of the cosmos itself. By the middle of the 20th century, it had become clear that curvature was not merely a feature of extreme environments. It was the architect of the universe on every scale. The first truly cosmic consequence of Einstein's theory emerged from solutions found by Alexander Friedmann in the early 1920s. Friedmann assumed that the universe, when viewed on the largest scales, was uniform in all directions. This symmetry simplified the field equations, and what emerged startled the scientific world. Space-time did not need to remain static. It could expand or contract. The distances between galaxies could change as part of the universe's geometry. Einstein initially doubted this result, believing that the cosmos must be eternal and unchanging, but observations soon shifted the conversation. When Edwin Hubble measured the light of distant galaxies, he discovered that they were receding from the Milky Way. Their light was stretched toward the red, a signature of cosmic expansion. The universe was growing. Friedmann's solutions had predicted the behavior decades before the evidence arrived. Curvature, not force, guided the evolution of the cosmos. This expansion unified the story of the universe under general relativity. If the cosmos was expanding now, it must have been denser and hotter earlier. The field equations, traced backward through time, pointed toward a state of enormous density. What began as a purely theoretical consequence of Einstein's geometry became the foundation of the hot Big Bang model, later confirmed through observations of the cosmic microwave background. The faint radiation filling space, discovered in the 1960s, carried the imprint of the early universe's geometry. Small variations in this radiation mapped the seeds of future structures. Where the radiation was slightly denser, galaxies would one day gather. Where it was thinner, cosmic voids would stretch. The entire cosmic web emerged from the interplay between matter and curvature. As telescopes improved, astronomers found that massive structures such as galaxy clusters acted as gravitational lenses, bending light from more distant sources. This bending produced distorted arcs, multiple images, and even full rings when alignment was perfect. These patterns were not approximations. They were exact consequences of photons following geodesics in curved spacetime. The geometry encoded the distribution of mass within the lens, including the unseen mass known as dark matter. By studying the distortions, astronomers could map mass that emitted no light. The gravitational lensing of clusters allowed scientists to chart the invisible architecture of the cosmos with remarkable precision. Once again, geometry revealed reality. At even larger scales, the motion of galaxies traced the influence of curvature. Dense regions attracted more matter, forming filaments that stretched across hundreds of millions of light years. Voids expanded between them. Computer simulations that included general relativity produced cosmic structures strikingly similar to those seen in surveys. The shape of the universe itself arose from the tug of curvature on matter over billions of years. No Newtonian model could reproduce this interwoven network. The geometry of spacetime was the blueprint. Closer to home, astronomers turned their attention to the centers of galaxies. Observations of stars orbiting the core of the Milky Way revealed motions so rapid that only a supermassive black hole could account for them. Over decades, researchers tracked these stars with increasing precision. Their trajectories, especially those of stars passing close to the central object, followed paths predicted by general relativity rather than Newtonian gravity. Time dilation, orbital precession, and the influence of strong curvature all appeared naturally in the data. These stellar motions provided some of the clearest evidence that Einstein's equations described gravity even in extreme environments. Then came a breakthrough in imaging. The Event Horizon Telescope, an array of radio observatories spread across Earth, captured the first direct view of the region surrounding a supermassive black hole. The image showed a bright ring shaped by photons orbiting near the event horizon. Its diameter and shape matched the predictions of general relativity with striking accuracy. The appearance of this ring was a direct manifestation of curved spacetime. Light, traveling along geodesics distorted by enormous mass, formed a structure that revealed the geometry around the black hole. The silhouette was not an object, it was spacetime itself. Even beyond these extreme environments, general relativity influenced everyday technologies. Satellites carrying atomic clocks orbited Earth at heights where gravitational time dilation differed measurably from clocks on the surface. Without relativistic corrections, the global positioning system would drift by kilometers within a single day. This dependence on Einstein's equations demonstrated that curvature mattered not only in cosmic realms, but in the routines of daily life. Radar ranging experiments further confirmed the theory. When signals passed close to the Sun on their way to distant planets, they took slightly longer to return. The delay matched the predictions of curved spacetime, showing that gravity influenced the paths of signals even when no matter lay in their way. The Sun's presence shaped the geometry, and the geometry shaped the travel time. No mechanism of force was needed, only curvature. General relativity also described the behavior of black holes themselves. The Schwarzschild solution revealed that a non-rotating black hole had a precise geometry with an event horizon marking the boundary from which light could not escape. The Kerr solution extended this to rotating black holes, showing that rotation twisted spacetime, dragging inertial frames around the object. Observations of matter in accretion disks revealed signatures of this frame dragging. The geometry near spinning black holes shaped not only light, but the plasma orbiting them at nearly the speed of light. These observations formed yet another consistent thread in the tapestry woven by general relativity. As evidence accumulated across decades, one fact became unavoidable. Curvature did not merely describe extreme phenomena, it shaped everything. The orbits of planets, the bending of starlight, the expansion of the universe, the structure of galaxies, the timing of clocks, and the appearance of black holes all emerged from the same geometric principles. Space and time were not containers. They were participants. Their shape dictated motion. Their evolution guided the cosmos. Yet even with its breathtaking success, general relativity left open one frontier. It could describe the universe at large scales with unmatched accuracy. But at the smallest scales, where quantum effects dominated, it could not provide a complete picture. The union of geometry and quantum mechanics remained unsolved. Before that frontier could be approached, physicists had to understand how relativity behaved in the presence of quantum laws. By the time general relativity had proven itself across the cosmos, physics stood upon two towering pillars. One was Einstein's geometric description of gravity, governing planets, stars, galaxies, and the unfolding of the universe itself. The other was quantum theory, a framework that described the behavior of atoms, particles, and the smallest constituents of matter with astonishing precision. Each theory was stunningly successful. Each had withstood every experimental test placed before it. Yet the two refused to merge. Their visions of reality were built upon foundations that could not be reconciled without deeper insight. Where general relativity described smooth curvature, quantum mechanics described discrete quantities and probabilistic behavior. Where relativity treated spacetime as a continuous fabric, quantum field theory required a fixed background to define particles and interactions. The clash did not lie in failed predictions. It lay in the fact that both theories worked so well that neither could be dismissed. This tension emerged most clearly in environments of extreme density and energy. Near a black hole, where curvature grew enormous, The classical equations predicted a singularity, a region where densities and curvatures climbed without bound. No known law could describe what occurred beyond that point. The singularity was not a physical entity, but a sign that space-time, treated as continuous, had reached a domain where classical geometry could no longer stand alone. Quantum effects must intervene, but quantum theory, built upon fixed space-time, could not describe the moment when space-time itself became dynamic. At that boundary, the two pillars of physics both demanded authority. A similar problem appeared in the earliest moments of cosmic history. As astronomers traced the universe backward in time, guided by the field equations, they found that density and temperature rose to extraordinary heights. The expansion appeared to begin from a state of extreme curvature known as the Big Bang singularity. Yet this singularity could not represent a literal moment in physical history. It was an indication that classical space-time, with its smooth geometry, could not describe the earliest stages of the universe. Once again, relativity approached a domain that belonged to quantum mechanics, but quantum mechanics lacked the tools to describe a space-time that was not fixed, but alive with curvature. Physicists confronted these problems, knowing that both theories were accurate within their domains. General relativity described every gravitational phenomenon ever observed. Quantum mechanics predicted atomic spectra, particle behavior, and electromagnetic interactions with astonishing precision. The conflict arose only when both theories were needed at once, in places where curvature was extreme and quantum behavior unavoidable. These situations revealed the boundary of modern physics, a frontier where neither theory could fully replace the other. The first hints of a deeper connection appeared in black hole thermodynamics. In the 1970s, Stephen Hawking applied quantum principles to particles near a black hole's event horizon. He found that vacuum fluctuations, inevitable in quantum theory, interacted with the curved geometry in such a way that black holes emitted radiation. This Hawking radiation implied that black holes had a temperature and entropy, quantities normally associated with thermodynamic systems. The idea that black holes could radiate slowly and eventually evaporate showed that general relativity and quantum mechanics could not remain isolated. Their predictions overlapped in non-trivial ways. But Hawking radiation raised a deeper paradox. If black holes evaporated completely, what happened to the information carried by matter that fell into them? Quantum theory required information to be preserved. General relativity offered no mechanism for that preservation. This information paradox did not contradict any experiment, because Hawking radiation had not yet been observed directly. But it exposed a conceptual gap. Somewhere within the fabric of physics, a deeper structure must reconcile the demands of both quantum theory and curved space-time. Different research programs approach this problem from different angles. One framework, known as loop quantum gravity, attempted to quantize space-time itself. Instead of treating geometry as smooth, it proposed that the fabric of space-time was made from discrete units. These units, woven together at extremely small scales, created a granular structure. In such a framework, singularities could be resolved because curvature never reached infinity. The early universe might have passed through a phase where quantum geometry replaced classical descriptions. But while mathematically elegant, loop quantum gravity lacked direct experimental evidence. Another approach, string theory, described particles not as points, but as vibrating strings embedded in higher dimensional spaces. Gravity emerged naturally as one of the vibrational modes. The theory unified all forces under a single framework, and at low energies, it reduced to general relativity. String theory offered mechanisms by which singularities could be smoothed and information preserved. It provided a potential path toward a quantum theory of spacetime. Yet its predictions remained out of reach experimentally, and its higher dimensional structure made it challenging to test. A more conservative line of research used effective field theory, treating general relativity as a low-energy approximation to a deeper quantum theory. This approach predicted small quantum corrections to gravitational interactions without attempting to quantize the geometry fully. These predictions were too small to detect with current technology, but they provided a consistent way to bridge the classical and quantum worlds without contradiction. Despite the differences among these programs, one requirement remained universal. Any successful theory of quantum gravity had to reduce to general relativity in the classical limit. All experimental evidence demanded this. Gravitational waves, orbital dynamics, lensing, time dilation, and cosmic evolution all agreed with the geometric description provided by Einstein. Any deeper theory had to preserve these successes while extending the description to domains where quantum effects dominated. Physicists accepted that nature might hold a deeper structure than either relativity or quantum mechanics described individually. Yet the absence of experimental contradictions meant that Einstein's theory remained the correct description of gravity in every measurable regime. The frontier where the two theories would meet remained beyond current observational reach. But that frontier did not weaken general relativity. It clarified its role. Gravity was geometric everywhere humans had been able to observe it. In the century since Einstein wrote his field equations, every test had confirmed the same message. Motion followed geometry. Time flowed according to curvature. Light bent because space-time bent. And the universe grew and evolved under the guidance of the metric that Einstein had uncovered. The quantum world offered mysteries yet to be solved, but it did not challenge the central truth of general relativity. It only hinted that geometry might hold even deeper layers waiting to be revealed. From the first moment Einstein imagined an observer drifting weightlessly in free fall, the nature of gravity began to shift. What had once appeared to be an invisible force acting across empty space gradually transformed into something deeper and far more elegant. After a century of observation, calculation, and experiment, the evidence now painted a single coherent picture. Gravity was not a pull. It was the shape of space-time. Geometry, not force, governed all motion. Every object in the universe, from grains of dust to clusters of galaxies, moved along paths carved by curvature. Every experiment ever performed confirmed this vision, revealing a cosmos where motion was the natural flow of space-time itself. In this geometric universe, a freely falling object required no cause to accelerate. It followed the straightest possible path through space-time, a geodesic determined by the mass and energy surrounding it. Standing still on Earth was not rest, it was resistance. The ground pushed upward, preventing one from following the curved path that space-time prescribed. The sensation of weight was a sign of defying geometry. What felt like force was simply the refusal to fall. This reinterpretation of motion became one of the most profound shifts in the history of physics. It replaced Newton's invisible pulling force with a geometric foundation built from the metric, the curvature, and the structure of space-time itself. This picture extended across all scales. In the solar system, planets traced orbits, not because the sun pulled them, but because the sun's mass had shaped the space-time around it. Mercury's orbit revealed this curvature most clearly, drifting slightly more each century than Newtonian gravity predicted. Einstein's field equations captured the drift precisely. Light passing near the sun bent not because it felt any attraction, but because it followed the shortest route through curved space-time. Observations during the 1919 eclipse confirmed this effect, showing that geometry alone guided the path of photons. As the decades unfolded, more tests deepened this understanding. Clocks placed on mountains ticked faster than clocks at sea level. Time itself responded to curvature. Radio signals took longer to travel near the sun. Their trajectories were lengthened by the shape of space-time. Satellites orbiting Earth required corrections from both special relativity and general relativity to maintain accurate timing. Without these corrections, global navigation systems would drift by kilometers each day. Gravity Probe B measured the subtle twisting of spacetime around Earth, confirming that rotation dragged inertial frames in exactly the way predicted by relativity. These experiments showed that relativity was not simply a theory of the distant cosmos. It governed the rhythms of everyday life. Beyond the solar system, the reach of Einstein's geometry grew even more astonishing. Observations of stars near the center of the Milky Way revealed the presence of a supermassive black hole. The paths of these stars, some whipping around the central region in a matter of years, provided a direct look into strong gravitational fields. Their orbits shifted and precessed exactly as relativity predicted. The intense curvature near the black hole controlled their motion with mathematical precision. When the Event Horizon Telescope captured the first image of the region surrounding a supermassive black hole, the geometric nature of gravity became visible. The bright ring corresponded to photons orbiting near the event horizon, following paths shaped entirely by curvature. The size and shape of this ring matched the predictions of general relativity. It was not an illustration. It was an observation of spacetime itself. Then came the gravitational waves. When LIGO recorded the tiny ripples produced by merging black holes, it detected spacetime in motion. These waves matched the expected signatures of Einstein's equations with remarkable accuracy. The inspiral, the merger, and the ring-down phases all carried the imprint of curved geometry. No alternative explanation fit the data. Gravitational waves provided direct evidence that spacetime was dynamic, capable of transmitting energy, capable of ringing like a physical entity. The detection of merging neutron stars extended this new astronomy by combining gravitational waves with electromagnetic signals, revealing the formation of heavy elements through the geometry of a catastrophic collision. On cosmic scales, the field equations guided the evolution of the universe itself. The expansion discovered by Hubble, the structure of the cosmic microwave background, the formation of galaxies, and the distribution of matter across the cosmic web, all emerged from the dynamic geometry described by general relativity. The Friedmann equations, derived from Einstein's framework, predicted an expanding cosmos long before evidence confirmed it. Every subsequent observation aligned with a universe shaped by curvature, not force. The unity of this picture remained striking. A single set of equations described the bending of light, the ticking of clocks, the orbits of planets, the structure of clusters, the behavior of black holes, the propagation of gravitational waves, and the expansion of the universe. No separate laws were needed. Geometry served as the foundation for all motion. Even the quest to unify relativity with quantum theory, though still unfinished, did nothing to weaken this picture. Any future theory of quantum gravity would have to reduce to general relativity in the classical limit. Every experimental test demanded it. The geometric description of gravity was too successful, too consistent, too deeply embedded in observation to be replaced. The quantum world hinted at a deeper structure, but that deeper structure would preserve Einstein's geometry wherever curvature remained smooth and measurable. After a century of tests, the verdict of the universe was clear. Einstein had revealed a truth that extended far beyond his own era. Gravity was not a force acting across distance. It was the curvature of spacetime itself. Objects moved not because they were pulled, but because the geometry of the universe guided them along natural paths. Time flowed according to curvature. Light bent according to geometry. The cosmos evolved under the structure encoded in the field equations. In this universe, understanding motion meant understanding spacetime. And understanding spacetime meant recognizing that the true engine of the cosmos was not force, but geometry.